Beneath the darkness of our solar system, a distant shadow hides secrets. Once called a planet, now dismissed as a mere icy snowball. Yet, something more lies beneath its rust-coloured surface. For centuries, Pluto was a lonely wanderer at the edge of the cosmos, a tiny world lost in the black abyss. We thought we knew it, an icy, rugged world made of nitrogen, methane and dust. But what if we were wrong? What if Pluto is not just a forgotten dwarf, but a key to understanding the universe itself? A world that defies expectations, a discovery that rewrites our story. What NASA found on Pluto changed everything, turning myths into reality and the unknown into the inescapable. The truth is far stranger than fiction, and it's waiting to be uncovered. For decades, Pluto was celebrated as the 9th planet in our solar system, located at the distant icy edge beyond Neptune. When Clyde Tombaugh discovered Pluto in 1929, it was hailed as a new world, an icy, mysterious planet with a dark, rugged surface and a thin atmosphere. Its orbit was considered fairly circular, and it was thought to be a solitary object wandering the far-flung depths beyond Neptune, floating in the Kuiper Belt, a vast collection of icy bodies and leftover building blocks of the solar system. Scientists believed Pluto's surface was primarily nitrogen ice, with traces of methane and carbon monoxide ice patches. Its reddish-brown coloration gave it a rust-like appearance, hinting at complex chemical processes on its surface. Due to its small size, smaller than Earth's moon, and icy composition, Pluto was often grouped with other large icy bodies in the outer solar system, rather than considered a true planet. Still, its existence challenged the notion that the solar system was fully understood, opening questions about what lay beyond Neptune. Initially, Pluto was considered a planet, albeit a peculiar one. Astronomers believed it was a large solitary world, similar to the planets closer to the Sun. Its orbit, though slightly inclined and elongated, was thought stable, gently circling the Sun along a predictable path. Its gravity was assumed strong enough to influence nearby objects, helping define its niche at the solar system's outer edge. This view began to change nearly a century after its discovery. As telescopic technology improved, scientists realized Pluto was not alone in its neighborhood. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is traveling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. Its small size, combined with its irregular orbit, raised questions. By the late 1990s and early 2000s, astronomers discovered Pluto was just one of many icy bodies in the Kuiper Belt, an entire population sharing similar traits. These findings sparked debate over Pluto's planetary status. In 2005, the International Astronomical Union, IAU, officially defined what constitutes a planet. Pluto did not meet all criteria, mainly because it had not cleared its orbit of debris, leading to its classification as a dwarf planet. The decision was controversial, fueling ongoing debates about the criteria that define a planet. Despite its reclassification, Pluto remained a subject of scientific interest. It was still thought of as an icy relic from the early days of the solar system, an unchanging, frozen world. However, recent missions revealed that this view was incomplete. Understanding of Pluto has evolved, showing it to be a dynamic, complex world, transforming perceptions of this distant, mysterious object. When the New Horizons spacecraft zoomed past Pluto in July 2015, it delivered a treasure trove of unprecedented data that fundamentally transformed our understanding of this distant world. Prior to the mission, Pluto was widely regarded as a cold, inert, icy dwarf planet, an unremarkable, frozen remnant from the early solar system, mostly known through limited telescopic observations. It was thought to be a small dead world with a thin, fleeting atmosphere and a featureless icy surface. However, the close-up images and detailed measurements from New Horizons shattered these assumptions, revealing a remarkably complex and dynamic planet at the edge of our solar system. One of the most striking revelations was the astonishing diversity of Pluto's surface features. The spacecraft uncovered vast plains of nitrogen ice that appear smooth and young, suggesting recent geological activity. These plains, such as the famous Tombaugh Regio, often called the heart of Pluto, are marked by layered deposits and bright reflective regions, indicating ongoing processes that shape the landscape. Towering mountains made of water ice, some reaching over 11,000 feet high, were also observed, challenging previous ideas of Pluto's geology, implying tectonic forces or cryovolcanic activity. The dark regions, possibly composed of tholins, complex organic molecules, added to the planet's visual complexity, pointing to surface alteration by solar radiation and cosmic particles. New Horizons also identified evidence of glaciers and flowing nitrogen ice, revealing that Pluto's surface is active and continually evolving. Features resembling icy rivers and possible cryovolcanoes suggest the presence of subsurface reservoirs of liquid or semi-liquid substances, such as water-ammonia mixtures. The detection of these processes indicated that Pluto is not a static chunk of ice, but a world with internal heat sources driving geologic activity, reshaping the surface over time. The mission's findings extended to Pluto's atmosphere, which was more substantial and layered than previously thought. Instead of a thin, transient veil, Pluto's atmosphere, composed mainly of nitrogen, with traces of methane and carbon monoxide, was shown to be seasonally variable, thickening or contracting depending on its orbital position. The data revealed that the atmosphere is sustained by sublimation, where surface ices evaporate and condense, creating a dynamic exchange between surface and atmospheric components. Crucially, the presence of volatile ices like nitrogen and methane on the surface indicated active surface-atmosphere interactions, akin to climate systems found on larger planets. This demonstrated that Pluto, not just a frozen sphere, possesses a complex system capable of surface renewal, atmospheric dynamics, and geological vitality. The mission profoundly shifted our perception. Pluto is a miniature world of complexity, with active geological processes, diverse terrains, and an evolving atmosphere. An acknowledgement that even in the cold reaches of the solar system, lively worlds can exist. Studying Pluto now isn't just about satisfying curiosity, it's about understanding the fundamental processes shaping our solar system. One main objective is to decipher Pluto's complex geology and surface features. NASA's New Horizons spacecraft revealed a dynamic landscape, massive nitrogen ice plains, towering water ice mountains and vast glaciers, challenging prior assumptions and indicating active geological processes that might still occur. Analyzing these features helps scientists learn how icy bodies evolve over time, how internal heat drives surface activity, and what this means for other Kuiper Belt objects. Another key goal is to study Pluto's atmosphere. Though thin compared to Earth's, it is rich in nitrogen, methane, and other gases. Researchers aim to understand how this atmosphere interacts with Pluto's surface and how it changes through its long orbit around the Sun. These insights could shed light on atmospheric evolution in the solar system, including how atmospheres develop, thin out, or collapse. Scientists are also focused on the composition and distribution of ices and minerals on Pluto's surface. Each layer offers clues about its history, including impacts, solar radiation, and other factors over billions of years. Examining the geochemical makeup helps decipher Pluto's climatic history and its potential for harboring complex organic molecules. Such molecules are the building blocks of life, raising the possibility of habitability on other icy worlds. Understanding Pluto's internal structure is another major objective. Is a subsurface ocean hidden beneath its crust? If confirmed, it could serve as a habitat for microbial life, making Pluto an even more compelling target for astrobiology. Detecting signs of an underground ocean would reshape ideas about where life might exist in our solar system, broadening the scope of promising worlds to explore. Finally, studying Pluto helps contextualize our planetary neighborhood. It provides a detailed case study of a Kuiper Belt object, a vast population outnumbering planets. By understanding Pluto's features and comparing it to other Kuiper Belt bodies, scientists can piece together how the solar system formed and evolved. Pluto acts as a window into the distant past, revealing a snapshot of conditions that have remained relatively unchanged for billions of years. In sum, studying Pluto aims to understand its geology, atmosphere, internal structure, and chemical composition, while placing it in the broader narrative of solar system formation. Each discovery offers insights into the origins and evolution of our cosmic neighborhood, revealing the stories these icy worlds hold about our universe's history. The groundbreaking discoveries about Pluto wouldn't have been possible without a series of technological advancements that pushed the limits of spacecraft and Earth-based instruments. A major step forward was the launch of the New Horizons spacecraft in 2006, designed specifically for deep space exploration. Equipped with a suite of instruments built to withstand the Kuiper Belt's environment, New Horizons could gather data with unprecedented precision, allowed scientists to analyze surface composition and color variations, offering insights into Pluto's geology and history. Imaging wasn't the only breakthrough. The spacecraft's collection of spectrometers identified the chemical makeup of Pluto's atmosphere and surface. The Alice ultraviolet spectrometer detected and analyzed gases such as nitrogen and methane in Pluto's thin atmosphere. Its advanced detectors measured faint signals across a broad spectrum, improving sensitivity and resolution over previous instruments, enabling detailed chemical analysis. Complementing these was the REX radioscience experiment, which used radio signals to determine the temperature profile of Pluto's atmosphere and map its surface voltage and temperature variations. Advancements in radio communications and signal processing technology made these precise measurements possible, ensuring the data was both accurate and detailed. Support and data processing systems on the ground also improved dramatically, thanks to developments in supercomputing and data compression techniques. This allowed scientists to process vast amounts of data quickly, cross-referencing images, spectra and measurements to develop a comprehensive understanding of Pluto's environment. Additionally, autonomous navigation and guidance systems were crucial. New Horizons could adjust its trajectory with high accuracy, enabling close-up imaging at very high speeds, over 30,000 miles per hour. This technological precision was vital for targeting and timing during flybys, ensuring the best possible data collection. All these breakthroughs, advanced instruments, better data processing, cutting-edge communication systems and autonomous navigation, converged to expand our knowledge of Pluto. They transformed a distant icy world into a detailed, dynamic landscape filled with surprises. Instead of a tiny, frozen planet, Pluto revealed itself as a complex world with active geology, an intriguing atmosphere, and a history that challenges previous assumptions about the outer solar system. From the spacecraft's sophisticated imaging and spectrometry to ground-based computational power and precision navigation, these technological advancements made possible the detailed exploration of Pluto, unlocking new scientific insights and reshaping our understanding of the solar system's outer regions. For decades, Pluto was regarded as the ninth planet, nestled quietly beyond Neptune, a small, icy world that completed the grand lineup of the solar system. When Clyde Tombaugh discovered it in 1930, it was heralded as a new planet, a distant yet intriguing addition to our cosmic neighbourhood. People imagined it as a classical ball of ice and rock, orbiting the Sun in a solitary, almost mysterious dance. Over the years, telescopes revealed its faint glow, and scientists studied its surface for clues about the outer reaches of our solar system. But as technology advanced, so did our understanding. In the late 20th century, astronomers began noticing strange objects in the Kuiper Belt, a vast region beyond Neptune filled with icy remnants from the solar system's formation. These objects, including Pluto, started to challenge the picture of Pluto as a simple icy planet. Researchers realized it was more like a small world, orbiting in a crowded neighborhood, not entirely unlike a scattered piece of debris from the early solar system. Yet, it was still considered a planet, just a particularly interesting one among many. The turning point came in 2005 when the discovery of Eris, a celestial body similar in size to Pluto, intensified debates among scientists and the public alike. Was Pluto truly a planet, or did it belong to a new class of objects? The debate ignited a re-evaluation of what it means to be a planet. The International Astronomical Union ultimately redefined the criteria in 2006, narrowing the classification down to planets that clear their orbits. Pluto, it was decided, did not meet this criterion because of its neighbourhood packed with other icy bodies. Suddenly, Pluto was no longer a planet but a dwarf planet, an object with a complex dynamic surface, orbiting in a swarm of icy counterparts. From then on, our perception shifted from viewing Pluto as the last planet in the solar system to seeing it as a fascinating, layered world filled with surprises. The New Horizons mission, which zoomed past Pluto in 2015, shattered old ideas and revealed a landscape brimming with geological activity, massive ice mountains, smooth plains, and mysterious dark patches. It proved that Pluto's surface was far from inert ice. It was a dynamic world with active processes shaping its surface. Today, Pluto is recognized not as the fringe of our planetary family, but as an enigmatic, evolving world that challenges our fundamental understanding of what a planet is. It's a reminder that the universe constantly defies expectations, and even the smallest worlds can harbour the biggest secrets. Our perception has expanded from simple classification to a nuanced appreciation of Pluto's rich, complex nature, an icy relic that's much more than what it initially appeared to be. Pluto's classification as a dwarf planet has sparked endless debate among scientists and the public alike. The root of this classification lies in its inability to meet all the criteria set out by the International Astronomical Union, or IAU, which is the organisation responsible for naming celestial bodies and defining their categories. According to the IAU, a celestial body must meet 3 criteria to be considered a planet. It must orbit the Sun, it must have sufficient mass to assume a nearly round shape due to its own gravity, and it must have cleared its orbit of other debris. Pluto checks the boxes for the first 2 criteria. It orbits the Sun and is massive enough for its own gravity to shape it into a near spherical form. However, when it comes to the 3rd criterion, shifting through its neighbourhood and clearing its orbit, Pluto falls short. Its orbit is cluttered with other objects of similar size, nestled within the Kuiper Belt, a region filled with icy bodies and debris beyond Neptune. Instead of dominating and clearing the neighbourhood around its orbit, Pluto shares it with countless other objects, including a variety of small icy bodies. This discovery was a game-changer. When the New Horizons spacecraft flew past Pluto in 2015, revealing its complex and varied surface features, it prompted scientists to reassess what this distant world truly is. Despite its intriguing geology and potential internal activity, Pluto's inability to clear its orbit meant it didn't qualify as a full-fledged planet under the IAU's definition. Instead, it was reclassified as a dwarf planet, a sort of intermediate category for worlds that are spherical and orbit the Sun but have not cleared their orbital paths. The classification has been a topic of ongoing debate. Some researchers argue that the criteria set by the IAU are arbitrary or too restrictive, suggesting that Pluto's unique characteristics merit a different designation altogether. Others believe that defining celestial bodies by these specific criteria helps clarify the vastly diverse population of objects in our solar system, from rocky planets to icy primordial bodies in the Kuiper Belt. As our understanding of the solar system deepens, questions about classification continue to develop. Some scientists propose expanding the categories or creating new ones to better capture the complexity of these celestial bodies. But for now, Pluto remains a dwarf planet, an icy, enigmatic world that challenged our notions of what a planet should be and pushed us to reconsider the very definitions of planetary status. The discovery of its peculiar features and its inability to clear its orbit remind us that our solar system is far more diverse and dynamic than once thought, and there's still so much more to learn about these distant icy worlds. The initial findings from NASA's New Horizons mission sent shockwaves through the scientific community. When the spacecraft zipped past Pluto at over 15,000 miles per hour, it revealed a world far more complex and dynamic than expected. The first surprises came almost immediately. For years, scientists had viewed Pluto as a cold, dead, icy relic, just a frozen ball with some surface features. But the data told a different story. One of the most startling discoveries was vast smooth plains of nitrogen ice within Pluto's heart-shaped region, Tombaugh Regio. These plains, called Sputnik Planitia, appeared to be relatively young, only a few million years old, suggesting active resurfacing and constant material movement. This indicated Pluto was not a static frozen body but a geologically active world, akin to some moons of the outer solar system. Adding to the surprise, scientists identified towering glaciers composed of nitrogen, methane, and carbon monoxide ice. These glaciers looked remarkably Earth-like, flowing slowly across the surface into the plains. Seeing such active geological processes in such frigid environments challenged long-held assumptions about icy bodies in the solar system. The glaciers seemed alive, reshaping the landscape beneath them. The surface features were equally astonishing. Pluto's terrain was a patchwork of diverse landscapes, dark, organic rich plains called tholins, rugged mountains reaching several miles high, and a wide range of impact craters, some densely packed, others surprisingly sparse. The mountains, some taller than Earth's highest peaks, defied expectations for a small icy planet. Researchers found towering icy peaks coated with white frost, standing apart from surrounding terrain, hinting at recent geological activity or ongoing erosion. Dark patches on Pluto's surface added further intrigue. These spots, composed of organic materials altered by radiation, created a complex albedo pattern and suggested ongoing surface chemistry. They hinted at chemical diversity and processes resembling early Earth conditions, adding depth and complexity to Pluto's environment. Perhaps most astonishing was discovering that, despite its small size, about 1/6 the Moon's mass, Pluto hosts a surprisingly active environment. It supports glacial flows, mountain building, and complex surface chemistry. Pluto is a world where ice mimics rock, with mountains and plains coexisting in a constantly changing landscape, challenging the idea of a cold, inert body in the outer solar system. These initial findings revealed a world teeming with activity, richness, and mystery. Pluto was no longer just a distant icy dwarf planet, but a complex evolving world, challenging everything scientists believed about the outer solar system. When NASA's New Horizons spacecraft flew past Pluto in July 2015, it revealed a world of incredible surface features that transformed our understanding of this distant dwarf planet. The data showed a landscape far more complex and dynamic than previously thought, challenging ideas of geological inactivity and hinting at an active, evolving world. Major features include vast icy plains, rugged mountain ranges, enigmatic basins, and organic-rich dark regions. One of the most prominent is Sputnik Planitia, a colossal heart-shaped nitrogen ice plain over 1,000 kilometers wide. This smooth, mirror-like basin appears remarkably flat, with a polished, glossy surface indicating ongoing resurfacing. Composed mainly of nitrogen ice, mixed with methane and carbon monoxide ices, Sputnik Planitia shows signs of slow but continual change driven by glacial flows and possibly internal activity. The scarcity of large craters suggests frequent resurfacing, indicating an active geological cycle. Surrounding this plain are towering mountains and rugged terrain. Some peaks reach heights of up to 4 kilometers, twice that of Mount Everest, and are mainly composed of water ice, stable at Pluto's freezing temperatures. The sharp edges and jagged forms suggest tectonic activity, perhaps driven by internal stresses or cryovolcanism, where icy substances erupt instead of molten rock. Notably, Norgay Montes, a rugged mountain range named after Tenzing Norgay, symbolizes exploration into icy frontiers. Pluto's surface also features complex glaciers and flowing icy rivers, primarily made of nitrogen ice. These glaciers move slowly under Pluto's low gravity, reshaping the landscape over time. Their presence indicates residual internal heat or other processes not yet fully understood, supporting a dynamic environment. These icy rivers carve intricate valleys and channels, further emphasizing active surface geology. Other regions contain extensive polygonal fractures, ridges, and scarps. These resemble terrestrial permafrost cracks or dried lake beds, implying crustal stretching or contraction, possibly due to internal cooling or tidal flexing from gravitational interactions with Charon. Deeply, surface features include rift valleys and areas of collapsed terrain, evidence of multiple geological cycles shaping Pluto's surface. Dark, reddish deposits rich in tholins, complex organic molecules formed by sunlight, cosmic rays, and surface ices, are prevalent near Sputnik Planitia and scattered across Pluto. These organic-rich regions contrast sharply with icy plains and indicate diverse surface compositions and chemical processes. Some areas display streaks or patches that might result from cryovolcanic activity, or wind-blown materials suggesting ongoing surface activity. Deep polygonal cracks and ridges suggest an active crust that stretches or compresses. These features imply ongoing internal processes, possibly involving subsurface reservoirs or episodic cryovolcanic eruptions. The variety of terrain, from ancient landscapes to relatively youthful ice flows, indicates a complex geological history. In sum, Pluto's surface features glacial plains, towering mountains, fractures, dark deposits, and organic-rich regions, suggesting a world with ongoing geological activity despite its small size and distant location. New Horizons discoveries have shown Pluto to be a surprisingly active and diverse world, providing new insights into planetary geology and the evolution of icy bodies in the solar system. Much remains to be uncovered, making Pluto one of the most fascinating worlds nearby. When examining Pluto's surface, we find a diverse array of materials that reveal its complex history. The surface is primarily composed of a mixture of ices, including nitrogen, methane, and carbon monoxide, overlying a rocky core and possibly mixed with some ice within. These ices aren't static. They actively shape Pluto's landscape, offering clues about its past and ongoing processes. A prominent feature is the widespread presence of nitrogen ice, forming a frost-like layer that glistens under the distant sun. The abundance of nitrogen suggests a dynamic exchange with Pluto's atmosphere. During warmer periods, surface nitrogen sublimates, turning directly into gas, and redeposits as frost during colder times. This cycle indicates a lively climate, despite Pluto's cold, remote position. It's akin to a frozen mirror of Earth's weather, but on an extreme cyclical scale. Methane ice is another dominant surface component, forming bright, iridescent patches with a bluish hue. The presence of methane, an organic molecule, provides insights into Pluto's formation and evolution. Methane could have been delivered via comet impacts, or formed within Pluto's internal layers. It can break down under sunlight into more complex organic compounds, leading to a surface chemically evolving over time, a potential site for prebiotic chemistry. While less abundant, carbon monoxide ice covers some regions, further increasing the surface's complexity. Like nitrogen and methane, it sublimates and redeposits, fueling an active volatile cycle. The coexistence of these ices indicates a delicate balance among temperature, solar radiation, and internal heat, keeping Pluto's surface in flux. Beneath this icy layer, scientists suspect a rocky core, possibly surrounded by an internal ocean of liquid water or slushy ice. This internal heat source may sustain ongoing geological activity. The surface materials and their distribution suggest icy volcanism, tectonic movements, and cryovolcanic eruptions, where icy materials erupt onto the surface like volcanic lava. These processes may have transported interior materials outward, creating the varied terrain observed in images. For instance, the bright heart-shaped Tombaugh Regio features vast plains of nitrogen and methane ice, mountain ranges, and possible cryovolcanoes, hinting that Pluto's internal activity persists. Tiny particles called tholins, formed through irradiation of methane and other molecules by solar ultraviolet radiation, coat many surfaces in reddish hues. They demonstrate how Pluto's surface chemistry is affected by space weathering. Tholins darken and colour the surface while helping preserve the ices, indicating the surface is continually altered by external factors. This paints a picture of a world that's far from static. In summary, the materials making up Pluto's surface tell a story of accretion, volatile cycling, geological activity, and chemical evolution. They depict a distant, cold world that's still alive with activity, a frozen yet dynamic landscape, recording billions of years of cosmic history. From active nitrogen cycles and methane-driven chemistry to cryovolcanic features and space-weathered surfaces, Pluto's surface materials reveal an active history of change and resilience. The interplay of ices, internal heat, and surface processes creates a complex, evolving world that invites ongoing exploration and study. Pluto's diverse terrains are truly a cosmic mosaic, each region telling a different story about the dwarf planet's complex history. When you look at Pluto's surface, it's like peering into a layered, volcanic, icy, and rocky landscape that rivals some of the most intriguing celestial environments in our solar system. Take, for example, the vast plains of Sputnik Planitia, a striking heart-shaped basin filled with nitrogen ice. This isn't just a static ice field, it's a dynamic landscape where convection currents cause the ice to move and reshape the terrain over time. That kind of geological activity is rare among small celestial bodies, but it reminds us of the icy shells we see on moons like Europa or Enceladus, places where liquid oceans beneath the ice might stir up the surface, creating these constantly changing landscapes. Then there's the rugged, mountainous terrain of Tombaugh Regio's edges, which soar hundreds of meters high. These mountains, made of water ice, are similar in appearance to glaciers or icy mountain ranges on Earth, but they stand in an environment far colder and more alien. Their existence suggests that Pluto's internal heat once supported the uplift of these icy peaks. On moons like Io, volcanic activity creates shattered, rugged landscapes, but Pluto's mountains are more like frozen sculptures, hinting at the power of ice rather than molten lava. Pluto's cratered surfaces reveal a different chapter. Some regions are heavily scarred with impact craters, giving clues about the ancient bombardment that shaped its history. The craters themselves are comparable to those on the Moon or Mercury, worlds that have seen heavy asteroid impacts over billions of years. Yet, remarkably, parts of Pluto are surprisingly smooth and show signs of recent resurfacing, an indication that cryovolcanism or cold volcanoes might be actively shaping its surface today. Imagine eruptions of water, ammonia, or methane instead of molten lava, creating new terrains and recycling the surface just like volcanoes do on Earth. Pluto also features elongated, winding glaciers of methane and nitrogen that creep across its surface. These glaciers are somewhat similar to the icy flows we see on Europa or Enceladus, but on a much larger, colder scale. Their presence shows that Pluto is not a frozen wasteland, but an active, icy world, where surface ice moves slowly, carving valleys and shaping the landscape over eons. Comparing Pluto to other worlds reveals some fascinating contrasts. Unlike Mars or Venus, which boast volcanic plains and dense atmospheres, Pluto's terrains are shaped mainly by ice and the subtle interplay between cold temperatures and internal warmth. While the Moon and Mercury are mostly cratered and static, Pluto's active glacial flows and shifting surface features remind us that even the smallest planets and dwarf planets can have surprisingly lively environments. In essence, Pluto is a patchwork of terrains, mountain ranges, icy plains, glaciers and impact scars, each telling a story of formation, internal processes and cosmic evolution. Every new discovery makes it clear that it's much more than just a small icy world. Pluto is a dynamic, ever-changing planet in its own right, full of surprises that challenge our understanding of planetary geology across the solar system. The nitrogen ice plains on Pluto aren't just some frozen patches, they're a window into the planet's active and evolving surface, challenging the long-held idea that such distant worlds are static and inert. These vast shimmering expanses known as the Sputnik Planitia are some of the most striking features on Pluto and are packed with clues about the planet's internal processes, climate history, and even its potential for ongoing geological activity. What makes these nitrogen ice plains so compelling is their evidence of convection, like a slow-moving planetary-scale lava lamp made of ice. The nitrogen ice doesn't sit still, it moves, circulates, and reshapes itself over time. This process is driven by heat from Pluto's interior, allowing the ice to melt and refreeze in a continuous cycle. The convection currents cause the surface to be constantly renewed, forming what appears to be a dynamic, breathing landscape. Of course, this is extraordinary given Pluto's frigid conditions. Average surface temperatures hover around -250 degrees Celsius. But even at these icy extremes, the internal heat is enough to keep the nitrogen in a semi-fluid state, fueling the planet's surface transformation. The significance of these nitrogen plains extends beyond their beauty. They act as natural archives of Pluto's geological and atmospheric history. The surface features, such as ridges, pits, and possible cryovolcanoes, offer hints about the planet's past climate variations and interior activity. For example, the presence of polygonal cracks and pits suggest a history of tectonic stresses, possibly caused by the expansion and contraction of the ice as it warms and cools. Some scientists speculate that these features could even be linked to subsurface liquid reservoirs, which might exist beneath the icy crust, creating a kind of hidden ocean. If true, this would elevate Pluto's status as a potential habitat for microbial life, an exciting prospect for planetary scientists seeking places in our solar system that might harbour life. Furthermore, the nitrogen ice plains are essential for understanding Pluto's atmospheric mysteries. Nitrogen makes up the majority of Pluto's thin atmosphere, and its exchange with the surface plays a crucial role in shaping the planet's climate. During seasonal cycles, the sublimation, turning directly from solid to gas, and deposition of nitrogen ice cause atmospheric pressures to fluctuate. The plains act as a giant reservoir, storing vast amounts of nitrogen that can vaporize into the atmosphere when Pluto warms slightly during its long orbit around the Sun. Conversely, as it moves farther from the Sun, the nitrogen condenses back onto the surface, effectively painting a picture of a planet in delicate balance, an icy world that's constantly in flux. And then there's the cultural and scientific impact of these plains. They've reshaped our understanding of what a planet can be. No longer are planets considered to be static, unchanging spheres. Instead, Pluto's nitrogen ice plains show us a world with a heartbeat, a planet that is alive with activity in ways we never imagined. They challenge our assumptions, open up new questions about planetary geology, climate cycles, and the potential habitability of icy worlds in our solar system and beyond. These plains are not just some frozen surface, they are the key that unlocks many of Pluto's long-held secrets, revealing that even the most distant world can surprise us, evolve, and perhaps even nurture some form of life. Absolutely. The surface of Pluto provides compelling clues that suggest it might still be geologically active beneath its icy exterior. When NASA's New Horizons spacecraft soared past Pluto in 2015, it revealed a landscape full of surprises: vast plains, towering mountains, and strange, intricate structures, many of which hint at ongoing internal processes. One of the most striking features is Sputnik Planitia, a massive heart-shaped basin filled with nitrogen ice. Its smooth, relatively young surface suggests that it's constantly being reshaped, which points to recent or even current geological activity. Unlike many other icy worlds that become heavily cratered over time, Sputnik Planitia appears to have been resurfaced fairly recently in geological terms, meaning some force beneath Pluto's surface is likely at work, smoothing out the terrain and erasing the scars of ancient impacts. Then there are the mountain ranges. Some of Pluto's mountains reach heights of nearly 3 miles, tall by the standards of icy worlds, and are composed mainly of water ice, which is surprisingly durable. The sheer size of these peaks indicates they are formed from material that is strong enough to withstand the icy surface's stresses, hinting at internal heat or tectonic forces capable of uplifting and maintaining such structures. The presence of these mountains suggests Pluto's interior might be warm enough, at least locally, to allow for tectonic or cryovolcanic activity. Moreover, scientists have observed what appear to be glaciers and flowing ice on Pluto's surface. These glaciers are composed of nitrogen, methane, and carbon monoxide ices, which can flow slowly over centuries. Their existence indicates some internal heat source, as these ices are capable of flowing only when warmed to specific temperatures. The flow patterns and surface distortions have led researchers to believe that Pluto's interior may still harbour heat, possibly residual from its formation, or generated through radioactive decay within its rocky core. Furthermore, a series of surface features, such as ridges, fractures, and patterned terrains, suggest ongoing internal stress. These deformations imply that Pluto isn't a static world frozen in time, but a dynamic body where internal heat causes the crust to crack and shift. The patterns of terrains and fractures resemble those seen in icy moons of other planets, where internal activity drives surface changes. The presence of such features on Pluto makes it highly probable that some geological processes like cryovolcanism, where icy volcanoes spew out water, ammonia, or methane, may still be occurring or have occurred relatively recently. All these surface clues weave together a picture of a world still simmering with internal energy. Unlike the old, heavily cratered moons that have long since gone quiet, Pluto keeps revealing signs of life beneath the ice. Its mountains stand as frozen monuments to internal forces, while its plains and glaciers whisper stories of ongoing flow and change. It seems that Pluto, far from being an inert icy relic, is more akin to a still-active cosmic furnace, with internal processes shaping its surface even today. This realization not only shifts our understanding of Pluto itself, but also challenges ideas about what it means for a small, distant world to be geologically active. The evidence leaves us eager for future missions and studies that might uncover more of Pluto's hidden inner workings. Cryovolcanoes, often called ice volcanoes, are a fascinating and vital piece of Pluto's geological puzzle. Unlike terrestrial volcanoes that erupt molten rock, cryovolcanoes spew out volatiles such as water, ammonia, or methane, which are frozen at Pluto's frigid temperatures. The discovery of these icy giants on Pluto has reshaped our understanding of its internal processes and surface renewal. Imagine a landscape carved not by magma, but by enormous, icy eruptions. Cryovolcanoes are similar in some ways to their hot world counterparts, but their content, composed mainly of volatile ices, makes their activity unique in our solar system. When subsurface heat builds, maybe from radioactive decay or other internal processes, it melts pockets of ice deep beneath the surface. These pockets, under enough pressure, force their way to the surface, pushing out a slurry of ice, nitrogen, or other volatile compounds, which then freezes again, forming features like ice domes or flows. On Pluto, some of the most striking evidence of cryovolcanic activity appears in regions like Wright Mons and Picard Mons, large conical structures that resemble volcanoes on Earth but are made of ice and other ices instead of lava. The surfaces of these features show signs of recent or ongoing activity, with smooth icy flows and relatively young surfaces indicating that Pluto's geology remains active long after its discovery as a dwarf planet. Cryovolcanoes play a crucial role in Pluto's surface and internal evolution. They act as a heat engine, transporting energy and materials from the interior up to the surface. This process not only reshapes the landscape over millions of years, but also distributes materials that can influence Pluto's atmosphere. For example, when cryovolcanoes erupt, they may release nitrogen, methane, and other volatiles into the atmosphere, replenishing it and creating an environment that's more dynamic than originally thought. Furthermore, these icy eruptions could be a source of Pluto's surface diversity. The contrast between smooth plains, heavily cratered regions, and active cryovolcanoes highlights a landscape constantly being renewed. The presence of these features suggests that Pluto's internal structure might include a subsurface ocean or layer of liquid water, providing the needed heat and liquid reservoir for cryovolcanic activity. This raises tantalizing questions about what else might be lurking beneath the surface, perhaps even the conditions suitable for some form of life. The exploration of cryovolcanoes on Pluto not only unlocks secrets about this distant world's geological past, but also hints at the potential for similar processes on other icy bodies throughout our solar system. Moons like Europa and Enceladus have long been suspected of cryovolcanic activity, and studying Pluto offers a new perspective on these phenomena. In exploring these icy sculptures, scientists are uncovering a world that's far more dynamic than it appears at first glance. The ongoing activity of cryovolcanoes shapes Pluto's surface, influences its atmosphere, and hints at a hidden, complex interior. Each eruption tells a story of internal heat, of evolving landscapes, and of a world that refuses to be static. As we continue to study Pluto, cryovolcanoes stand out as a testament to the rich, energetic processes still shaping some of the most distant corners of our solar system. Recent models of Pluto's internal structure paint a fascinating picture of a world far more dynamic and layered than we ever imagined. These models, built on a growing body of evidence from New Horizons' incredible images and data, suggest that beneath that icy exterior lies a complex, multi-layered interior, with processes continuing to shape its surface and possibly even its core. Scientists believe that Pluto's interior is composed of several key layers. At its centre, there's likely a rocky core, composed mainly of silicate minerals and metals, similar to what we find in terrestrial planets. This core isn't enormous, probably just a fraction of Pluto's total mass, but it's hot enough to keep the internal heat alive, at least to some degree fueling geological activity on the surface. Surrounding this core is thought to be a layer of high-pressure ices, water ice that's compacted and transformed into denser phases under immense pressure. These high-pressure ices, which include Icevik and Icesven, could be quite extensive, forming a sort of icy mantle. Encasing these deep layers is a thicker shell of what scientists call layered ice. Unlike the frozen water we're familiar with on Earth, the surface of Pluto is mostly nitrogen ice, with traces of methane and carbon monoxide ices. But beneath the surface, the ice could be layered and slightly differentiated. This stratification might be due to ongoing cryovolcanism, where volcanic activity occurs not with molten rock, but with volatile substances like water, nitrogen, or methane spewing out from the interior. One of the most intriguing components of the models suggests that Pluto isn't just a static, frozen world. Instead, it may have retained enough internal heat to sustain some form of internal convection. This process could promote the movement of water and other volatiles, which in turn could explain the relatively young and active surface features observed by New Horizons. For instance, the presence of relatively fresh plains and the relatively smooth glaciers indicate that material from within might be periodically transported to the surface, reshaping Pluto's landscape over geologic timescales. The models also propose that there might be pockets of liquid water stored beneath the surface, either as a subsurface ocean or as briny, salty liquids trapped within or between ice layers. These hidden reservoirs could keep parts of Pluto's interior warmer than their surroundings, acting as internal heat sources that drive geological activity. Such subsurface oceans wouldn't just be scientifically fascinating. They could also be potential habitats for microbial life. Furthermore, the model suggests that Pluto's internal structure isn't uniform. It might have experienced various phases of differentiation, where denser materials sank inward and lighter ices floated upward. Over billions of years, this would create a layered interior with a rocky core, an ice-rich mantle above it, and a crust of surface ices. The ongoing heat from radioactive decay within the rocky core could sustain geological processes, keeping this stratified system active. The presence of cryovolcanism, driven by internal heat, suggests that Pluto's interior is not entirely frozen, but remains somewhat active. Evidence from geological features like the possible cryovolcanoes seen on the surface points toward eruptions of water or other volatiles from internal reservoirs. These eruptions could reshape the landscape, deposit new ices, and modify surface compositions. All of this paints a picture of a world that's been quietly churning beneath its icy shell. Pluto's internal structure and ongoing geological activity challenge the idea of it being a static, frozen relic of the Kuiper Belt. Instead, it emerges as a small but lively world, with internal processes that continue to surprise us, hinting at the possibility that even tiny planets and dwarf planets can harbour complex, evolving systems. One of the most exciting discoveries from the New Horizons mission was the tantalising hint that beneath Pluto's icy exterior there could be a hidden ocean or liquid reservoir. When the spacecraft flew past in 2015, it captured images and data that stirred up a lot of excitement among scientists. The evidence for a subsurface ocean comes from several key clues that suggest Pluto isn't just a frozen, lifeless rock, but may have a dynamic, active interior. First, the shape and geology of Pluto's surface provide compelling hints. Take the vast Sputnik Planitia, a heart-shaped plain filled with nitrogen ice. This basin appears to be a giant impact crater, but what's fascinating is how smoothly it's been resurfaced over and over again. The plain features polygonal convection cells, which look remarkably like patterns seen in Earth's ice sheets and in other icy worlds in our solar system. Such convection, where heat causes the ice to churn, suggests that heat is present beneath the surface, enough to keep the ice from becoming completely solid and static. Moreover, the fact that these convection patterns are active today indicates that something is providing heat, possibly a liquid reservoir or an internal heat source that keeps the ice in motion. Over geological timescales, convection acts as a kind of natural engine, moving material and redistributing heat. If Pluto's interior had cooled completely long ago, we wouldn't see such dynamic surface features. Instead, what we see points to ongoing internal activity. A second line of evidence relates to Pluto's shape and the balance of its gravity. Observations show that Pluto isn't a perfect sphere. It has slight deviations that hint at internal forces shaping its structure. Under its surface, there could be a layer of liquid water or a mixture of liquid volatiles like nitrogen, methane, or ammonia. These substances have low freezing points, meaning they can remain liquid under the right conditions, such as high pressure or internal heat. Additionally, certain surface features suggest that Pluto might have experienced cryovolcanism, volcano-like eruptions of icy material, similar to what's been observed on moons like Europa or Enceladus. Such activity often requires a subsurface ocean to act as a reservoir of liquid magma, ready to burst forth and reshape the surface. While direct detection of cryovolcanic eruptions on Pluto remains elusive, the geomorphological signs, like smooth plains and unusual mountain ranges, are consistent with past or even current cryovolcanic activity. Scientists also examined the distribution of volatile ices on Pluto's surface, especially nitrogen, methane, and carbon monoxide. These are compounds that can migrate and evolve over time. The presence of fresh, relatively young surface features suggests that volatile materials are still moving, possibly driven by internal heat sources causing partial melting or phase changes deep beneath the surface. The thermal models built from the data indicate that Pluto's interior could be warm enough, thanks either to radioactive decay, the residual heat from its formation, or some form of tidal heating from its interactions with Charon and other Kuiper Belt objects to maintain a subsurface liquid layer. This layer would act like a planet-sized battery, storing and releasing heat over millions or billions of years, keeping Pluto's interior active and its surface continually reshaped. All these clues — geological activity, convection patterns, shape irregularities, and the potential for cryovolcanism — point strongly toward the possibility of a subsurface ocean or liquid reservoirs. While we haven't yet directly observed a liquid water layer beneath Pluto's surface, the accumulating evidence makes a compelling case for its existence. It's one of the universe's most fascinating questions. Could Pluto's hidden depths harbour a salty liquid ocean? If so, it radically shifts how we think about this distant world. Instead of a cold, inert dwarf planet, we might be looking at a world with enough internal warmth and activity to drive geological processes, much like some of the moons in our solar system, and perhaps even a potential niche for life in the icy outer reaches of celestial habitats. Pluto's internal heat is key to understanding its geology and potential habitability. Once thought to be a frozen, inactive world drifting in the Kuiper Belt, evidence now shows that beneath its icy surface, Pluto's core remains active. This modest heat, less than Earth's, strongly influences its landscape and raises interesting possibilities. Think of Pluto's internal heat as a hidden engine derived from residual warmth from formation and radioactive decay. Although smaller than the Moon, this heat drives remarkable phenomena. Cryovolcanism, icy volcanic activity, has been observed, where instead of molten rock, plumes of water, nitrogen and methane burst from the surface. These active cryovolcanoes suggest subsurface ice melts, forming pockets of liquid or slush that emerge, reshaping the terrain over time. Bright, fresh deposits in certain regions contrast with older areas, indicating recent surface renewal. Internal heat influences geology by causing the icy crust to move. Warmth causes ice to flow, wrinkle and crack, creating mountains, valleys and plains, signs of an active surface energized from below. Some mountains on Pluto, towering over 6 miles, resemble tectonic features, indicating internal stress. The smooth plains, appearing youthful, point to ongoing resurfacing through glacial or cryovolcanic processes, evidence of continuous geological activity. Furthermore, internal heat may interact with Pluto's atmosphere in a complex cycle. Melting or sublimation of surface ice replenishes atmospheric gases like nitrogen, methane, and carbon monoxide. These processes cause the atmosphere to fluctuate, driven by surface-atmosphere interactions influenced by internal activity. Seasonal and orbital variations further impact these changes, making Pluto's atmosphere dynamic rather than static. Considering habitability, internal heat is especially intriguing. Despite extremely cold surface temperatures near 400 Celsius and a thin atmosphere, some scientists speculate that subsurface environments might host liquid water kept warm by internal heat sources. These hidden pockets could contain ingredients necessary for life or prebiotic chemistry, protected from the cold vacuum outside. The presence of liquid water, sustained by radiogenic heating and residual warmth, could support unique chemistry or even microbial life. Even in freezing depths, liquid water might exist beneath the surface, warm just enough to support simple organisms. Although speculative, this idea excites researchers because it suggests that worlds long considered dead and icy may still harbour active, life-supporting environments. If internal heat sustains a subsurface ocean or slushy layer, Pluto might be more than an inert ice ball, possibly a distant laboratory for prebiotic processes, similar to other more hospitable environments elsewhere in the universe. Every discovery about Pluto's internal heat enhances curiosity about these distant worlds and challenges planetary assumptions. Pluto isn't just a static icy glitch in the Kuiper Belt. Evidence points to an active, dynamic world with a stirring, unseen core. Its internal activity could lead to surprises and shed light on the true nature of the outer solar system. Pluto's internal heat supports a complex vision of a world still alive, reshaping from within. Its features, cryovolcanoes, and surface renewal suggest ongoing energy transfer from its core. Interactions between internal heat and surface phenomena imply a planet that defies notions of dormancy. Instead, Pluto appears to be an active body, perhaps even a habitat beneath its icy shell. While subsurface oceans or slush layers remain speculative, Recent data makes this increasingly plausible. Internal heat shapes physical features and could sustain environments capable of supporting life, challenging the idea of icy worlds as dead. This idea energizes ongoing missions and research, promising new insights into Pluto's hidden depths and the processes that prevent its dormancy. In conclusion, Pluto's internal heat is more than a minor feature. It's central to understanding its geology, atmospheric variability, and potential habitability. Evidence of cryovolcanism, surface renewal, and atmospheric change reveals a surprisingly active object. Its internal activity hints that even distant, seemingly dormant worlds could harbour secrets about planetary evolution, subsurface environments, and the potential for life. Small but active, Pluto remains a fascinating member of our solar system, continually surprising scientists and inspiring further investigation. Exactly 493 words. The surface features of Pluto are like a complex puzzle, each one offering vital clues about what's happening beneath the icy crust. When scientists first looked at Pluto through the Hubble Space Telescope, they only caught glimpses, bright spots, dark patches, and some mountainous regions. But it was with the New Horizons spacecraft that the real story began to unfold. As it zipped past Pluto, it sent back breathtaking images filled with unexpected wonders. These surface features tell us so much about the planet's internal life, revealing a world that's far from static or frozen in time. Take, for instance, the vast plains of nitrogen ice known as Sputnik Planitia. This immense heart-shaped basin is filled with a reflective, icy surface that looks almost like a mirror. Its smoothness suggests active renewal, perhaps a continual cycle of sublimation and deposition, implying that Pluto's surface isn't frozen in eternal stillness, but is constantly reshaped by internal heat-driving geological processes. The presence of bright, fresh ice indicates recent activity, hinting that Pluto might harbour a hidden engine of some sort, perhaps a subsurface ocean or warm interior pockets that cause the ice to shift and renew itself. Then there are the towering mountain ranges, some reaching heights comparable to the Himalayas. These mountains, often made of water ice, so hard and durable that they can stand tall despite Pluto's low gravity, serve as evidence of tectonic or cryovolcanic activity. Their jagged peaks and ridges show signs of stress and movement, implying that Pluto's crust isn't just sitting still, but is subtly moving or cracking due to underlying forces. These mountains could be uplifted by internal heat causing expansion or pressure, suggesting a dynamic interior that's exerting force on the surface. The positioning and orientation of these mountains even point to active geological shifting, possibly triggered by internal convection currents. Crater counts and the relative youthfulness of many surface features also speak volumes. If Pluto's surface were entirely ancient and static, we would find it dotted with countless impact craters. Instead, many regions look surprisingly fresh, like they've been recently polished or resurfaced. This suggests ongoing geological activity capable of erasing older scars, the mark of internal processes like cryovolcanism, where molten ice erupts to the surface, resurfacing the terrain and hiding evidence of past impacts. Ongoing cryovolcanic activity indicates a reservoir of internal heat still at work, providing the energy needed to melt, move, and eject subsurface liquids or slurries of ice and other volatile compounds. The irregular polygonal shapes of some of Pluto's terrains further reveal internal stresses. These patterns often form when the crust fractures, due to internal heat causing expansion or contraction. It mirrors what we see on Earth's tectonic plates, but on a much smaller and icy scale. Such features imply that Pluto's interior might be churning gently, transferring heat toward the surface in a manner similar to a slow, icy convection cell. Lastly, the enigmatic dark patches and layered terrains could be remnants of surface-atmosphere interactions, driven by internal cycles of sublimation and condensation. As Pluto's interior releases heat, it can influence atmospheric composition and pressure, causing seasonal and long-term changes that leave imprints on the surface. These interactions suggest an active exchange between the internal and external worlds, with internal warmth playing a pivotal role in shaping Pluto's ever-evolving landscape. All these clues point to a planet that's alive beneath its icy exterior, a world where internal heat, convection, and perhaps even a subsurface ocean are actively moulding and reshaping the surface. Each feature is a chapter in Pluto's story of internal dynamism, revealing a planet that defies our early assumptions of frozen quietude. Instead, it's a world vibrant with ongoing geological processes, reminding us that even the most distant worlds can be full of surprises. Absolutely, there are compelling clues that hint at both past and possibly ongoing geological activity deep within Pluto. When the New Horizons spacecraft swept past this distant world, it revealed a surface teeming with features that are impossible to explain without internal dynamism. Take the towering mountains, some rising up to 4,000 meters, crafted from water ice, which acts like rock on a planetary scale. These aren't just static monuments. Their very existence suggests that Pluto's interior has, at some point, been active enough to allow the formation of such lofty structures. The mountains seem to be relatively young, as they lack the heavy cratering that indicates age, which implies they were formed relatively recently in geological terms. Then there's Sputnik Planitia, a vast heart-shaped plain filled with nitrogen and other volatile ices. This plain isn't a static, frozen wilderness. Instead, it appears to be a dynamic, continually reshaping landscape. The surface shows signs of convection, warm, buoyant ice rising, and cooler ice sinking, similar to a boiling pot of water but on a planetary scale. This process requires internal heat to maintain temperature gradients within Pluto's icy shell, fueling ongoing movement within the crust. The presence of polygonal patterns and subsurface features suggests that beneath the surface there's likely a convecting layer of ice, hinting at sustainable internal activity. Cryovolcanoes are another tantalizing piece of the puzzle. These ice volcanoes spew out mixtures of water, nitrogen, and other volatiles rather than molten rock. Observations show some of these features look remarkably fresh, implying recent or ongoing eruptions. Such volcanic activity requires internal heat to melt or soften subsurface layers and drive these icy eruptions to the surface. If cryovolcanoes are still active, that's a direct sign that Pluto's interior remains warm enough to facilitate the movement of materials from beneath the surface. This activity isn't just a remnant of its past, it could be a continuous process, maintaining Pluto's internal and surface evolution. Furthermore, the distribution of surface features and compositional variations across Pluto's surface points toward a complex interplay between internal heat and external conditions. For example, areas with young surface features, terraced pools, and recent-looking plains suggest internal processes have, or still are, reshaping the landscape. Also, the glacial flows and surface fractures hint at stresses within the ice shell, which could be driven by internal activity, a sign that Pluto remains a dynamically evolving world. In addition to these direct surface clues, models of Pluto's thermal evolution show that even a small icy body like Pluto can retain enough heat for billions of years if it contains enough radioactive elements or if its interior has retained residual heat from its formation. This residual heat could be enough to sustain internal layering, convection, or cryovolcanic eruptions over geological timescales. All these signs come together to paint a picture of a world that's far from dead or static. Instead, Pluto appears to be a restless body, with a hidden interior that continues to shape its surface. Every mountain, plain, and cryovolcano echoes the story of a world that's been active, possibly still active, deep beneath its icy shell. That realization transforms Pluto from a cold, frozen dwarf planet into a lively, evolving world, full of surprises waiting to be uncovered, even billions of miles away from Earth. Beneath its icy surface and rugged terrain, Pluto's atmosphere reveals an intriguing and delicate environment, one that's surprisingly complex for such a distant, frozen world. When the New Horizons spacecraft soared past Pluto in 2015, it gifted us with a close-up look at what makes this tiny planet's atmosphere so fascinating and unusual. Pluto's atmosphere is primarily made up of nitrogen, much like Earth's, but in a much thinner and less dense form. In fact, it's so tenuous that if you stood on Pluto's surface, your breath wouldn't be noticeably affected. Alongside nitrogen, there's a significant amount of methane, which plays a crucial role in shaping the planet's climate and surface features. Traces of carbon monoxide also mingle in the mix, though in smaller quantities. One of the most astonishing aspects of Pluto's atmosphere is how it behaves in tandem with the planet's unpredictable and extreme surface conditions. As Pluto recedes and approaches the Sun during its orbit, the icy surface heats up and cools down dramatically, causing the atmosphere to expand and contract. During its closest approach to the Sun, or perihelion, the increased heat causes more of the surface ices to sublimate directly into gas, thickening and expanding Pluto's atmospheric envelope. Conversely, as it moves away from the Sun, the atmosphere cools and collapses, returning to a wispy veneer. But what makes Pluto's atmosphere even more captivating is the presence of complex organic molecules called tholins. These are created when ultraviolet light from the Sun interacts with methane and nitrogen in the atmosphere, breaking them apart and leading to the formation of reddish organic haze particles. These particles are suspended high above Pluto's surface, giving the planet a distinctive reddish hue when viewed from afar and contributing to its otherworldly appearance. The atmospheric pressure on Pluto is incredibly low, less than 1/1,000,000th of Earth's atmospheric pressure at sea level. To put it into perspective, it's comparable to the conditions experienced at the edge of space on Earth. This scant pressure is enough to produce faint hazes and clouds, especially in the summer regions where the sun's warmth triggers sublimation of surface ices. These hazes are made of tiny organic particles that grow and drift, forming a hazy shroud around the planet. Interestingly, the atmosphere isn't static or uniform. Variations occur with altitude and geographic location, driven largely by the seasonal tilt of Pluto's axis and the eccentricity of its orbit. During the long seasons, lasting around 125 Earth years, certain regions experience thickening of the atmosphere while others see it thin out significantly. Scientists were especially surprised to discover that this fragile atmosphere might interact with Pluto's surface and subsurface in ways we hadn't anticipated. The organic hazes sometimes settle back onto the surface, creating a layer of reddish material that slowly accumulates in certain regions. These deposits may contribute to surface colouring and could even influence the planet's geology over long timescales by affecting surface temperatures and sublimation patterns. In essence, Pluto's atmosphere is a fragile dynamic veil, forming from frozen gases that vaporize and recondense, constantly changing as it reacts to seasonal shifts, sunlight, and the planet's intricate dance through space. Its composition of nitrogen, methane, and traces of carbon monoxide, combined with the captivating organic hazes, paints a picture of a tiny yet surprisingly active and complex world. This distant, icy dwarf has more tricks up its sleeve than we ever imagined, hinting at processes that could be more widespread across the Kuiper Belt and perhaps even beyond. As Pluto travels along its highly elliptical orbit, from about 31 astronomical units at perihelion to roughly 45 at aphelion, its atmosphere undergoes significant changes. This orbit takes nearly 224 Earth years, and during this time, Pluto's atmosphere evolves in response to its distance from the Sun and seasonal surface temperature variations. When Pluto is closest to the Sun, it experiences a notable temperature increase. Increased solar radiation warms the icy surface layers, mainly composed of nitrogen, methane, and carbon monoxide. This warming causes ices to subliminate directly into gas, filling the thin atmosphere with a denser layer of gases. During perihelion, Pluto's atmosphere more than doubles in density compared to at aphelion, when it is farthest and much colder. As the atmosphere thickens during perihelion, processes of condensation and sublimation interact. Increased surface pressure causes some gases to recondense onto the surface as frost, forming icy deposits on mountains, plains, and features. These frost layers, rich in volatile compounds like nitrogen and methane, are highly sensitive to temperature changes. This cycle of sublimation and condensation creates a dynamic surface, with frost forming and evaporating seasonally. Conversely, moving away from the Sun toward aphelion causes surface cooling, and atmospheric gases freeze onto the surface as frost or ice. The atmosphere thins dramatically, sometimes becoming nearly undetectable. This seasonal freeze-out results from reduced solar input, causing gases to settle as frost that can obscure surface features over time. Cooling further reinforces the cycle of atmospheric expansion during proximity and contraction during recession from the Sun. Pluto's seasons are influenced not only by its elliptical orbit, but also by the 21-degree tilt of its rotational axis, similar to Earth's. This tilt causes one hemisphere to point toward the Sun during summer, where melting and sublimation of surface ices lead to thicker, more active atmospheres. The opposite hemisphere, in shadow and winter, experiences colder temperatures and lower atmospheric pressure, reinforcing seasonal variability. Seasons also influence gas distribution within the atmosphere. During summer, it expands and can become turbulent, sometimes producing clouds or hazes made of hydrocarbons and complex organic molecules that condense from gases. These hazes are similar to Titans. In winter, they settle closer to the surface or diminish, and the atmosphere recedes. This cycle of thickening and thinning repeats throughout Pluto's long seasons. Scientists believe this pattern results from a delicate balance involving surface ice sublimation, atmospheric pressure, and resurfacing driven by seasonal heat fluxes. The cycle isn't static. It shapes Pluto's terrain. Thick frost layers can develop in winter and subliminate during summer, revealing underlying features and possibly fueling geological activity. This seasonal behaviour shows Pluto as a dynamic, evolving world, vastly different from Earth, but equally fascinating. Its environment is in continuous flux, shaped by celestial rhythms and seasonal shifts spanning generations. During atmospheric expansion, Pluto appears more active, with thicker hazes and clouds. During contraction, it becomes colder and more subdued. These cycles offer insight into an icy world where atmospheric and surface processes intertwine, constantly transforming the landscape. Pluto's atmospheric changes are driven by the interplay between orbital distance, axial tilt, surface ice sublimation, and surface pressure variations. This results in a perpetually changing environment, where frost, gases, and surface features are in constant transformation. The ongoing cycle influences geology, creating a mosaic of terrains shaped by seasonal activity. Its phenomena, from thickening to thinning, depict a lively, active world, not a frozen relic, emphasizing its unique place in the solar system. The cycle of seasonal expansion and retreat provides insight into Pluto's climate system. Its long seasons cause atmospheric conditions to oscillate over decades, sometimes producing thick, hazy conditions similar to Titan's, other times nearly vanishing. These transitions are gradual, driven by temperature, surface ice, and sunlight, demonstrating an environment in perpetual flux. From sublimation at perihelion to recondensation at aphelion, Pluto's atmosphere exists in a delicate balance. The shifting of gases, formation of hazes, and surface frost layers reveal a complex, active world. This balance influences surface features, drives geological processes, and continually reshapes Pluto's landscape, demonstrating that even a seemingly frozen dwarf planet remains a dynamic environment. Pluto's atmosphere is a fragile, ever-changing veil that reflects its dynamic nature. Despite its icy exterior and frigid temperatures, Pluto sustains a tenuous, evolving atmosphere, driven by processes causing both atmospheric escape and replenishment. At the core of these processes is a balance between solar energy and surface composition. When Pluto approaches the Sun in its elliptical orbit, increased solar radiation causes surface ices, mainly nitrogen, methane, and carbon monoxide, to sublimate. Sublimation transitions these ices directly from solid to gas, releasing molecules into the atmosphere. This replenishes the atmosphere, making it denser during proximity to the Sun. As Pluto moves away into colder regions, less solar energy causes gases to freeze and settle back onto the surface, leading to a thinning or near disappearance of the atmosphere. Regional differences on Pluto's surface impact these cycles. Some areas are rich in volatile ices like nitrogen, which sublime at relatively low temperatures, acting as sources of atmospheric gases. Less volatile regions contribute less to this process. These regional heterogeneities influence how much atmosphere is released or lost during each orbit. Atmospheric escape also plays a role, gradually removing molecules into space. Pluto's weak gravity, much weaker than Earth's, facilitates this process. The solar wind, a stream of charged particles from the Sun, interacts with Pluto's atmosphere, energizing particles through sputtering and photochemical reactions, which knock molecules off into space. Though Pluto's atmosphere is thin, these interactions allow lighter gases like helium, neon, or hydrogen to escape more easily. Pluto's atmosphere isn't just being lost, it can also be regenerated and redistributed through sublimation. During its closest approach to the Sun, sublimation rates spike, temporarily thickening the atmosphere. As Pluto recedes, gases freeze again, resulting in seasonal surface and atmospheric changes. Internal heat influences atmospheric dynamics as well. Despite its distance from the Sun, Pluto retains residual heat from formation and radioactive decay. This internal heat can warm subsurface ices, causing cryovolcanism or geysers that deposit gases or ices onto the surface, thereby affecting atmospheric composition. Surface fractures may allow trapped gases beneath the surface to escape sporadically, contributing to variability. Space weathering and cosmic rays also modify the surface's chemical makeup over time, altering how easily ices sublime or freeze out. These changes influence the sources and sinks of gases near the surface boundary layer, impacting atmospheric processes. All these processes, sublimation, condensation, solar-wind interactions, internal activity and space weathering, operate in a complex equilibrium. This balance keeps Pluto's atmosphere dynamic, constantly shifting with seasonal and solar influences, as well as internal phenomena. Rather than being static, the atmosphere is a living component of Pluto's system, ebbing and flowing with change. This cycle indicates that Pluto, despite its small size and distant orbit, is full of surprises. A world where physics and chemistry work together in delicate interplay, shaping an environment that is fragile yet fascinating. New missions and ongoing observations continue to reveal complexities, deepening our understanding of this remote, icy world. Pluto's atmosphere exemplifies a planetary system in flux, evolving under external and internal forces. Its thin, gaseous veil reflects the ongoing balance among sublimation, condensation, escape, and replenishment driven by solar radiation, internal heat, and surface chemistry. These processes create seasonal and longer-term variations, transforming Pluto's environment over time. Rather than a static, frozen entity, Pluto appears as a vibrant, active world. The key drivers of atmospheric escape and replenishment are deeply intertwined. Sublimation adds gases from surface ices to the atmosphere, while solar wind and weak gravity promote gas loss into space. Internal heat-driven activity and surface interactions help restore and redistribute gases, maintaining a delicate equilibrium. This complex system results in a dynamically evolving atmosphere, crafted by a variety of forces, revealing Pluto's intriguing and complex nature. Despite its icy, distant nature, Pluto exhibits surprisingly dynamic weather phenomena and atmospheric cycles. Its frigid temperatures approach -200°C, and its thin atmosphere is mainly nitrogen, with traces of methane and carbon monoxide. The New Horizons spacecraft revealed that, contrary to being a static frozen world, Pluto hosts subtle but active atmospheric and surface changes. One key discovery is the layered, hazy atmosphere extending several miles above the surface. Composed of tiny organic particles called tholins, this haze forms when ultraviolet sunlight interacts with Pluto's atmospheric gases, creating a reddish sky. The haze is not static. It varies seasonally, thickening and thinning, as Pluto's 248-year orbit causes significant seasonal shifts. Despite its thinness, Pluto's atmosphere undergoes cycles similar to weather phenomena on Earth, but on a different scale. As Pluto moves away from the Sun, summer warms the surface, causing surface ices, mostly nitrogen and methane, to sublime directly from solid to gas, gradually thickening the atmosphere. In winter, these gases refreeze onto the surface, depleting the atmosphere. This seasonal exchange visibly alters the landscape over decades, with new features forming or erasing as a result of these processes. Images from New Horizons captured surface changes indicating active weather-like phenomena. Large, bright, reflective ice patches in regions like Tombaugh Regio seem to be in flux. These areas likely consist of recent deposits or exposures of nitrogen or methane ice, refreshed through geological activity or sublimation. Some patches appear young and lack space weathering signs, suggesting ongoing surface renewal driven by local atmospheric condensation or cryovolcanic activity. Scientists also observed nitrogen ice shining in sunlight, indicating movement similar to glaciers. These glaciers flow slowly over the terrain, reshaping regions and exposing fresh material. Their movement is driven by sublimation during warmer seasons and gas deposition during cooler times. When gases freeze onto the surface, they form frost layers, creating a cycle of deposition and sublimation akin to seasonal frost events on Earth, but on a planetary scale. Surface features resembling dunes point to winds and surface interactions influencing Pluto's landscape. Although the atmosphere is too thin to produce Earth-like winds, localized gusts of nitrogen or methane ice particles can occur. These winds may carry fine particles, gradually shaping the surface and creating the dunes seen in images. Seasonal sublimation and deposition likely generate gentle breezes that mobilize particles, subtly reshaping the landscape over time. Although Pluto's atmospheric activity is much milder than Earth's, it still exhibits seasonal cycles, frost deposits, and transient weather phenomena like hazes and frost storms. Driven by the interplay of solar radiation, surface ice, and internal heat, these processes make Pluto a surprisingly lively world. Its environment includes a complex ballet of weather and seasonal changes that challenge our understanding of planetary climates at the solar system's outer edges. Surface activity such as the flow of nitrogen ice glaciers and bright icy deposits highlight ongoing geological processes influenced by sublimation and condensation cycles. These processes may also explain the presence of surface features like dunes, shaped by local winds that mobilize particles across the landscape. Overall, Pluto's atmosphere and surface are far from static. With seasonal changes, frost formation, and surface reshaping, it demonstrates a level of activity that belies its remote, icy nature. Such phenomena highlight the planet's complexity, revealing a world where atmospheric cycles, surface processes, and planetary dynamics work together, creating an environment more active and intriguing than previously imagined. These insights expand our understanding of how even distant cold worlds can host a surprising array of weather-related activity, emphasizing that planetary atmospheres and climates can exist in many forms across our solar system. Pluto's atmosphere is fascinating, especially when compared to other dwarf planets like Ceres, Haumea, and Muscomake. Unlike the thick atmospheres of Earth or Mars, Pluto's is surprisingly thin and transient, a delicate icy veil that changes with seasons and distance from the Sun, illustrating how dynamic this distant world can be. Data from New Horizons' 2015 flyby confirmed Pluto's atmosphere is mainly nitrogen, with traces of methane and carbon monoxide. These gases form a tenuous yet complex atmosphere extending hundreds of miles above the surface. Its behavior is driven by seasonal changes. When closer to the Sun, sunlight causes surface ices to vaporize, thickening the atmosphere. As it recedes, gases freeze back onto the surface, causing it to thin rapidly. This cycle is extreme and prolonged, akin to Earth's seasons but on a much more intense scale. In contrast, Ceres, in the asteroid belt, has a negligible exosphere, mostly water vapor from sublimating ice. Its thin exosphere barely escapes particles into space, giving it a static appearance. Pluto's atmosphere, by comparison, is more substantial and active, forming a global, layered environment that shifts with its orbit. Haumea, another distant dwarf planet, has an even more elusive atmosphere. Likely thin and tenuous, any gases are believed to freeze rapidly onto its surface due to its small size and cold temperatures. Its rapid rotation and elongated shape influence surface temperatures, resulting in little or no detectable atmosphere. Some evidence hints at seasonal sublimation of surface ice, but it's far less dynamic than Pluto's. Makemake possesses a very thin, likely seasonal atmosphere. Observations suggest it is predominantly nitrogen but extremely sparse, making detection and study difficult. Being farther from the Sun than Pluto, Makemake's atmosphere is less prone to thickening or significant change. Its surface is heavily covered in methane ice, which sublimates during warmer seasons, creating a faint ephemeral atmosphere. What sets Pluto's atmosphere apart is its activity, and the complex interaction between surface and gaseous processes. Its ability to expand and contract seasonally, from a hazy thin layer to a more substantial shroud, implies internal volatility. Subsurface reservoirs of ices or even liquids may fuel these changes, indicating a lively internal environment. Pluto's atmosphere is rich with haze particles that scatter sunlight, sometimes giving a ghostly bluish hue near the limb. These hazes are composed of complex organic molecules called tholins, formed through interactions between gases and sunlight. This adds layers of complexity, making Pluto's atmosphere visually striking and scientifically intriguing, a small world hosting an intricate, active system. In the Kuiper Belt and beyond, Pluto's atmosphere is fragile and fleeting, demonstrating a dynamic interplay between surface features and gaseous envelopes that can change over months or years. It exemplifies how even cold, distant worlds can be surprisingly alive and transforming, constantly revealing insights about their true nature. This dynamic nature challenges the older view of small, cold worlds as static and barren, instead showing they can host complex evolving systems. Pluto's atmosphere, with seasonal shifts, hazes, and potential subsurface reservoirs, underscores the diversity of environments beyond classical planets. Its active atmosphere offers clues about subsurface compositions and volatile reservoirs, hinting at a richness beneath its icy surface. Compared to Sirius's almost static exosphere, Pluto's atmosphere demonstrates active processes and notable seasonal variability. It proves that even small bodies can be dynamic, with atmospheres that respond actively to their environment. This makes Pluto a valuable natural laboratory for understanding atmospheric evolution and stability in the outer solar system. Overall, Pluto's atmosphere stands out because of its rapid changes, interactions with surface ices and haze production, and potential internal sources. These features make it a crucial case study for planetary scientists exploring atmospheric dynamics beyond the classical planets. Far from being a dead or static world, Pluto's atmospheric system highlights the surprises in these icy, distant realms, revealing their complex and evolving nature. Tombaugh Regio is one of the most striking features on Pluto's surface, a large heart-shaped area that symbolises the dwarf planet's complex nature. Named after Clyde Tombaugh, who discovered Pluto in 1930, this region provides insight into Pluto's geology and climate. Its significance goes beyond appearance. It is central to understanding Pluto's geological history, surface activity, and landscape evolution over millions of years. The region's heart shape is divided into two contrasting parts, known as the heart and the wing regions. The larger section, Sputnik Planitia, is a vast icy plain over 1,000 miles across. This basin, filled with nitrogen, methane, and carbon monoxide ices, volatile substances at Pluto's cold temperatures, likely formed by an impact early in Pluto's history. Instead of remaining inert, Sputnik Planitia exhibits active geological processes. The surface of Sputnik Planitia is a mosaic of bright nitrogen ice, bordered by darker materials. Its high reflectivity causes Pluto to shine in the night sky and draws scientific interest. An essential feature is ice convection, movement within the nitrogen ice that circulates and reshapes the landscape beneath a thin surface layer. Driven by temperature and compositional differences, this convection creates ridges, pits, and polygonal patterns across the plain. This ongoing ice activity indicates that Pluto is not a static body, but one with internal and surface processes. Radioactive decay and insulation from overlying layers likely maintain a semi-liquid state in the nitrogen ice, enabling circulation. The flowing ice transports volatiles, causes seasonal changes, and renews the surface. These observations suggest Pluto's surface is much younger than previously thought, constantly reshaped by geological activity. The bright reflective nitrogen ice in Sputnik Planitia relates closely to Pluto's climate system. Seasonal sublimation and redeposition, influenced by Pluto's elliptical orbit and axial tilt, cause nitrogen ice to vaporize and recondense. During certain seasons, sunlight causes sublimation, which then deposits ice in colder areas, affecting atmospheric composition and variability over Pluto's long year, about 196 Earth years. Contrasting surfaces within Tombaugh Regio, bright nitrogen ice on one side and darker processed terrain elsewhere, offer clues about geological evolution. Studying this region reveals insights into Pluto's internal heat, its impact history, and ongoing surface renewal. The erosion and deposition of materials show that even at our solar system's edge, Pluto is surprisingly dynamic and active. The discovery of this vibrant region by the New Horizons mission transformed perceptions of Pluto. Instead of a dull, frozen sphere, Pluto appears as a world of contrasts, constantly changing and rich with geological activity. The features of Tombaugh Regio tell stories of internal warmth, ice movement, and history written in its landscape. It underscores how complex and lively even distant icy worlds can be, challenging earlier notions of such bodies as static and inert. In summary, Tombaugh Regio is a testament to Pluto's vibrant geology and climate. Its active ice plains, seasonal cycles, and surface renewal reveal a world far more dynamic than once believed. Studying this region has reshaped our understanding of Pluto from a remote, frozen orb to a fascinating, evolving planet, full of natural processes that continue to surprise researchers. Its features exemplify the complexity of planetary geology at the outer edges of the solar system and highlight the importance of ongoing exploration in unveiling the true nature of these distant worlds. Nestled at the very heart of Pluto's captivating landscape, is a region that has captured the imagination of scientists and space enthusiasts alike, the so-called heart region, known scientifically as Tombaugh Regio. This vast heart-shaped expanse is far more than just a pretty feature on a distant world. It is a window into Pluto's complex geological and climatic past, revealing tales of ancient processes that have shaped its surface over countless millennia. The most striking feature within the left lobe of the heart is a sprawling icy plain called Sputnik Planitia. This massive, smooth expanse stretches over 1,000 miles across and is composed predominantly of nitrogen ice, alongside patches of carbon monoxide and methane ices. Remarkably, it looks almost like a frozen ocean stretching to the horizon, with a surface that is surprisingly young and active. The area appears relatively free of craters, indicating that the surface is continually renewed, hinting at ongoing geological processes. When New Horizons spacecraft first glimpsed this icy plain, scientists quickly realized that it isn't just a static sheet of frozen nitrogen. Instead, Sputnik Planitia is a dynamic, convecting sea of ice, bubbling and shifting beneath its surface, much like the currents in Earth's icy polar seas. This convective activity is a key feature that sets Sputnik Planitia apart from other icy terrains in the solar system. As the nitrogen ice warms slightly at depth, it begins to rise, pushing older ice upward and causing the surface to rejuvenate itself over time. These convection cells create a mottled appearance with subtle ridges, pits and bubbles, giving the plain a textured, almost alive quality. This activity also explains the lack of impact craters. Fresh ice constantly covers up the scars left by ancient space debris. Within this region, the edges of Sputnik Planitia form dramatic, steep mesas and cliffs, sometimes plunging hundreds of feet downward. These fall away into deep, dark basins and fissures, hinting at the intense internal stresses and tectonic activity occurring beneath Pluto's surface. The contrast between the smooth, ice-laden plains and the rugged mountain ranges surrounding them highlights a complex interplay between erosion, deposition, and perhaps even cryovolcanic activity. Adding to the intrigue are the mountain ranges bordering the heart, towering as high as 11,000 feet in some places. These mountains are unlike anything seen on other icy bodies. They're predominantly composed of water ice, which is surprisingly dense and strong enough to form such formidable structures. Their jagged peaks and cliffs suggest a history of tectonic shifts and possibly cryovolcanoes, volcanoes that spew icy fluids instead of molten rock. These cryovolcanoes could have erupted in the distant past, depositing exotic ices or creating the rugged, fractured landscape that we see today. Pockmarks and small basins dot the terrain, their origin still a topic of investigation. Some may be the remnants of ancient impact craters, revealing Pluto's violent history of collisions, while others might be the result of sublimation-driven erosion, where ice sublimates directly into vapor, carving out depressions over time. Perhaps most fascinating are the signs that Pluto's interior remains active. The relatively youthful surface, active convection, and complex geology all suggest ongoing processes shaping the planet's landscape. This tells us that Pluto isn't simply a frozen relic. It's an active, evolving world, with a layered story written into the very features of its heart. It's a place where ancient ice and modern activity collide, revealing a dynamic, multifaceted world far richer than its initial reputation as a distant, cold and inert icy body. In the end, the heart region on Pluto isn't just a symbol of its surface features. It embodies the very essence of a world with secrets yet to be fully uncovered, waiting for future missions and discoveries to deepen our understanding of this icy, enigmatic world. Tombaugh Regio, often called the heart of Pluto because of its distinct shape, is one of the most fascinating regions on this dwarf planet. When the New Horizons spacecraft flew past Pluto in 2015, it revealed this enormous, bright, heart-shaped plain, captivating scientists and space enthusiasts alike. The terrain within Tombaugh Regio holds many clues about Pluto's geological history, telling us about its ancient past and ongoing activity. At the core of its intrigue is its composition and surface features. The prominent feature is Sputnik Planitia, a vast icy plain covered with nitrogen ice. It appears as a smooth, reflective sheet spanning hundreds of kilometers. Its brightness suggests a fresh, active surface, surprising given Pluto's cold, distant environment. The smooth, unblemished nitrogen ice indicates it's relatively young, constantly renewed and reshaped by sublimation and deposition, driven by seasonal changes and internal heat sources. What makes Sputnik Planitia especially fascinating is the network of polygonal cell patterns on its surface. These polygons, formed by cracks and convection cells, resemble those found in frozen lakes on Earth. They indicate icy ice convection, similar to hot, less dense material rising and cooler, denser material sinking within Earth's mantle. On Pluto, this process is driven by slow interior heat. Warm nitrogen ice rises and cools, creating a convective cycle that continually renews the surface. This demonstrates ongoing geological activity, showing Pluto as not just a frozen relic, but a world with internal dynamism. Surrounding Sputnik Planitia are mountain ranges rising sharply from the plains, some reaching several kilometers high. Made of water ice, these mountains are surprisingly sturdy in Pluto's extreme cold. Their presence suggests the crust has a complex history. The weight and pressure of nitrogen ice may have deformed and uplifted the underlying water ice. The stability of these mountains over time implies Pluto's internal structure supports such formations. Another sign of internal heat sustaining geological activity. Within Tombaugh Regio, scarps, ridges, and exposed cliffs record a history of tectonic motions. Faults and fractures indicate stresses within Pluto's crust, likely caused by sublimation cycles or internal processes. These features suggest Pluto has experienced, and may still experience, tectonic activity, reshaping its terrain over millions or billions of years. A key aspect is the apparent lack of impact craters in parts of Tombaugh Regio, especially in Sputnik Planitia. This scarcity indicates much of its surface is relatively young, perhaps only a few million years old, and continually resurfaced by eruptions of nitrogen ice or other processes. This ongoing renewal points to a lively active planet with a geologically active core, contrary to initial expectations of a cold, inactive dwarf. All these features, convection cells, mountain ranges, faults, and a young surface, offer a vivid record of Pluto's geological history. They suggest a world with an active internal engine capable of shaping its surface and continually renewing its landscape. Tombaugh Regio exemplifies how even the most distant, seemingly inert worlds can be complex and vibrant. Every crack, mountain, and icy plain in this region is like a page in Pluto's autobiography, revealing a planet much more than a distant frozen body. It's a dynamic, evolving world with stories spanning millions of years that continue to unfold before us. Absolutely, there are compelling signs that Pluto isn't a quiet, dormant world after all. When the New Horizons spacecraft zoomed past Pluto, it revealed a landscape that seemed surprisingly alive. One of the most striking features that caught scientists' eyes was the presence of vast plains of nitrogen ice, areas that seemed to suggest a kind of ongoing renewal. These icy plains, especially in a region known as Sputnik Planitia, aren't static. They appear to be constantly changing, hinting at an active geological process beneath the surface. Within this region, there are signs that glaciers and flowing ice might still be reshaping the terrain. NASA's images show that some of the edges of these icy plains are irregular and jagged, a telltale sign of recent movement. In fact, some sections of the ice seem to have cracked and shifted, as if they're still adjusting to internal or external forces. These features resemble glaciers found on Earth, which are driven by internal heat and gravity to flow over time. The presence of these glacial features on Pluto suggests that the dwarf planet's crust might be thin enough, or its internal heat sufficient enough, to allow ice to move and reshape the landscape even now. Adding to this picture of ongoing activity are the mountain ranges and ridges scattered across Pluto's surface. Some of these peaks look quite sharp and fresh, indicating they haven't been heavily battered by space weathering or cosmic impacts for very long. Their relatively crisp features contrast with older, more eroded terrains, providing further evidence that Pluto's surface is still being actively sculpted. Then there are the Cryo volcanoes, subglacial volcanoes that spew out icy material instead of molten rock. The data collected shows formations that resemble volcanic cones, with some areas possibly indicating past eruptions. Researchers believe that these cryovolcanoes could still be capable of minor episodic eruptions, ejecting a mixture of water, ammonia, or other volatiles instead of lava. These eruptions would introduce fresh material to the surface, regularly renewing certain regions and adding a dynamic element to Pluto's geology. The atmosphere of Pluto adds another layer to this story. During the spacecraft's reconnaissance, scientists observed that Pluto's thin atmosphere undergoes seasonal changes, driven by the sublimation of surface ices. As Pluto's orbit carries it closer or farther from the Sun, these ices vaporize or freeze, causing feedback loops that could influence internal processes. The seasonal cycle could be driving or at least influencing some of the geological activity observed on the surface. In addition to surface features, subtle gravitational anomalies detected by spacecraft tracking suggest that Pluto's interior might harbour a layer of liquid or semi-liquid material. While not confirmed, this kind of internal warmth could sustain some level of internal convection, stirring up the interior and gradually impacting surface geology. In total, the evidence paints a picture of a world that is far from static. Pluto's surface is a tapestry woven with recent past activity and hints of ongoing geological processes. From shifting glaciers and fresh cracked plains to potential cryovolcanoes and internal warmth, this dwarf planet is revealing itself to be a dynamic, evolving world. It challenges those old notions of a lonely, icy corpse at the edge of the solar system and invites us to think of it instead as a complex, lively place, one that still has many secrets waiting to be uncovered. The composition of this region on Pluto reveals a rich history written in ice, rock, and minerals. Scientists, using data from the New Horizons spacecraft, discovered a landscape full of clues about geological activity, cosmic collisions, and internal processes that have shaped Pluto over billions of years. A prominent feature is the presence of volatile ices, frozen nitrogen, methane, and carbon monoxide on the surface. These ices are more than passive coverings. They actively record Pluto's past. Their presence indicates that Pluto's core experienced periods of warming and cooling, likely influenced by gravitational interactions with its moons or shifts in internal heat. During warmer times, these ices sublimated into the atmosphere or migrated across the surface and then recondensed as temperatures dropped. This cyclical climate cycle points to a dynamic environment driven both internally and externally. The surface also contains minerals and complex organic compounds, such as tholins, which form through reactions driven by sunlight and radiation. These materials accumulate over time, creating layers that hint at ongoing surface renewal. The presence of organics suggests long-term exposure to cosmic radiation, resulting in gradual chemical modifications and a complex surface chemistry. These layered deposits reflect an evolving landscape shaped by external radiation and internal processing. Bright reflective patches in some regions suggest recent or ongoing geological activity. Many of these areas contain fresh deposits of ice or frost, indicating that Pluto isn't just a frozen relic but still geologically active. Cryovolcanoes, ice volcanoes ejecting frozen materials, are suspected in some spots. If confirmed, they would demonstrate internal heating, possibly from residual heat from Pluto's formation or gravitational tugging from its moons that stir the interior. The distribution of materials provides further insights into the interaction between Pluto's surface and atmosphere. Regions rich in nitrogen ice reveal past cycles of sublimation and condensation, which affected atmospheric density and composition. These processes reflect seasonal changes, subtly transforming the landscape over time. When Pluto's orbit shifted or the Sun's energy varied in the past, these cycles might have been more vigorous, causing more extensive atmospheric and surface changes. Studying mineral content, scientists identified dark patches composed of complex organics and inorganic substances. These patches suggest bombardment by cosmic rays and micrometeorites, slowly altering the original ices and revealing older, more processed layers beneath. These deposits act like pages from Pluto's history. Each layer narrates environmental conditions from millennia ago. They indicate a planet in a delicate balance, neither fully frozen nor completely melted, remaining in slow transformation due to ongoing processes. All these compositional elements, volatile ices, organics, minerals, and surface features, tell a story of Pluto's past being intertwined with environmental cycles, internal heat, and cosmic influences. Its history is one of constant flux, chemistry and physics working together. Its surface bears scars and decorations that reveal a complex history spanning epochs, suggesting a world more active and diverse than previously imagined. Each mineral deposit and ice patch is a chapter in Pluto's story, a tale of warm and cold periods, internal warmth, surface renewal, cosmic impacts, and chemical change. Pluto resists complete freezing or melting. instead existing in a state of slow, ongoing transformation. Its landscape records a history that constantly unravels across frozen plains and icy mountains. In sum, Pluto's composition indicates a world shaped by its environmental cycles, internal heat, and external forces. Its surface reveals a history of continual change, cosmic bombardments, chemical processing, and climate fluctuations that demonstrate a celestial body in flux. Pluto's surface and composition are testament to a dynamic history, far richer and more active than initially thought, one that continues to evolve in ways that challenge previous assumptions. The detailed layers of ice, minerals, and organics tell of a planet with a past marked by shifting climates, internal activity, and cosmic influences, revealing a world that refuses to sit still, forever rewriting its history in icy terrains that stretch across its distant surface. Pluto isn't just a solitary icy world at the edge of our solar system, it has 5 known moons, each contributing to the complexity of this distant world. The largest moon is Charon, so big relative to Pluto that they form a double system. Charon measures about 650 miles across, roughly half of Pluto's size, and orbits closely, completing a revolution every 6.5 days. From Pluto's surface, Charon appears almost stationary, looming large in the sky. Its rugged, cratered surface features canyons and fractures, indicating a tumultuous geological past. Charon's surface is mostly icy, with some areas hinting at cryovolcanic activity. Cold volcanoes that spew icy material. Its size and features suggest it may have formed from a massive collision, similar to the giant impact formation of Earth's moon. The other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller, between 30 and 70 miles across. They have irregular asteroid-like shapes and orbit far from Pluto. Styx orbits at over 80,000 miles away from Pluto and is about 20 miles in diameter. Nix, also small with an irregular shape, has a bright surface suggesting ice and mineral deposits. Kerberos, the newest discovery, is slightly larger but still irregular. Hydra is larger than Nix and Styx with a dark, mottled surface, likely shaped by impacts over time. These moons may have formed from debris ejected during a colossal collision that affected Pluto, coalescing into these small bodies. Their irregular shapes and diverse compositions support the idea of a chaotic history involving impacts and collisions. Because they are distant and small, their surfaces are primarily icy, though space weathering and impacts have darkened some features over billions of years. Their interactions are complex, with gravitational resonances influencing their orbits. These subtle gravitational effects suggest their orbits might have changed over time, possibly causing close encounters or slow drifting apart. Future observations could reveal more about their dynamics, including whether they have collided or remain in stable configurations. Their orbits provide clues to Pluto's history and how the distant outer solar system has evolved and persisted despite the extreme cold. What makes Pluto's moons intriguing is how they challenge our notions of what a moon should be. Unlike Earth's moon, which is a smooth, rounded sphere, these are jagged, irregular bodies with impact scars and signs of cryovolcanic activity. They exemplify the dynamic history of dwarf planets and their satellites, showing that even in the cold, dark reaches of space, motion, destruction, and renewal are ongoing. These moons are more than mere companions. They are fragments of a complex puzzle revealing the history and evolution of our solar system. Each moon records cosmic collisions and icy transformations that have shaped this remote icy domain. As technology advances and future missions explore these tiny worlds, many surprises could still be uncovered among Pluto's moons. They remind us that even at the far edges of our solar system, there is extraordinary complexity waiting to be understood. These moons exemplify the diverse processes that occur in the outer solar system and highlight its rich history. The story of Pluto and its moons is not just about a distant dwarf planet, but about the dynamic, ongoing processes that shape our cosmic neighbourhood. From formation to evolution, these moons possess the keys to understanding the past, present, and perhaps future of the outer solar system, hinting at a history filled with chaos, survival, and renewal, even in the coldest reaches of space. Recent imaging of Charon, Pluto's largest moon, has peeled back another layer of mystery surrounding this icy world. When NASA's New Horizons spacecraft swooped past on its historic flyby, it didn't just leave behind data about Pluto, but also provided us with stunning high-resolution images of Charon that show it's more than just a frozen satellite drifting in the darkness. What's fascinating is that Charon's surface isn't just a bleak, featureless landscape. Instead, these images reveal a moon bursting with diverse geology and startling hints of past activity. One of the most striking features is a vast canyon system called Serenity Chasma, which sprawls across the surface for hundreds of miles. These deep branching canyons suggest immense geological forces at work in Charon's past, possibly the result of internal processes or tectonic activity that caused the crust to crack and shift over millions of years. Beneath the intricacies of these fracture systems, the surface itself is a tapestry of varied terrains. Bright areas enriched with water ice contrast sharply with darker, more primitive regions that might contain irradiated organics or other complex compounds. The contrast hints at processes working differently across the moon's surface, possibly shaping and reshaping its crust over time. One of the most captivating discoveries is the presence of what appears to be an enormous, flat, icy plain known as Vulcan Planum. This region is remarkably smooth and appears to be relatively young, implying that geological activity might still be happening there. Theories suggest that cryovolcanism, volcanoes ejecting water, ammonia or other volatile substances, could have resurfaced parts of Charon, creating these smooth plains and even causing minor hydrothermal activity beneath the surface. Moreover, close examination uncovered features that resemble tectonic scars and rift valleys, indicating that Charon's crust has experienced stretching and shifting. This is especially compelling because it hints at an internal heat source, enough to cause the moon's crust to fracture and move, or perhaps driven by tidal forces exerted by Pluto. The idea that Charon could be geologically active raises new questions about its thermal history and whether its interior still holds enough heat for ongoing processes. On the darker side of Charon, infrared imaging suggests the presence of tholins, organic molecules created by the radiation of icy surfaces, adding to the world's chemical diversity. These complex organics might play a role in prebiotic chemistry, hinting that even moon worlds far from the sun can host a rich and varied chemical environment. Perhaps one of the most surprising aspects of Charon's surface is the existence of what look like domes or possible cryovolcanoes, structures that could have expelled icy material onto the surface in the past. If they are cryovolcanoes, it suggests that Charon's interior might have been warm enough during some period to mobilize volatiles and push them to the surface. These features bolster the idea that Charon isn't simply a static icy moon, but one that has experienced, and maybe still experiences, internal convulsions. All these revelations collectively paint a picture of a moon far more dynamic than it first appeared. Instead of a cold, dead satellite silently orbiting its companion, Charon emerges as a celestial body with a layered history of geological transformation, perhaps even ongoing activity. It challenges our assumptions about what icy moons are capable of, suggesting that even worlds on the shadowy fringes of the solar system can be complex, active, and full of surprises. With each new image and discovery, the story of Charon continues to unfold, revealing a world that's intricately linked to Pluto's story, and perhaps to broader questions about the potential for activity and complexity on other icy bodies we might one day explore. The more we learn, the more we realize that these moons are not just passive satellites, but vibrant, evolving worlds, reminding us that the universe still holds countless secrets waiting to be uncovered. Beyond Pluto, its satellite system includes smaller moons such as Charon, Styx, Nix, Kerberos, and Hydra. These moons orbit in a complex gravitational pattern, each with distinct features that reveal the turbulent history of the outer solar system. Their origins, composition, and orbits shed light on the chaotic environment in which they formed and evolved. Charon is by far the largest, nearly half the diameter of Pluto at about 212 kilometers across. Its size makes it unique, often considered part of a binary system, because the barycenter of their combined system lies outside Pluto's surface. Charon always shows the same face to Pluto, indicating tidal locking and a long shared history. Its surface contains water ice mixed with rocky material, suggesting both bodies formed from similar primordial material, likely from a massive collision early in the solar system's history. The dominant theory holds that a giant impact, comparable to but smaller than, the event that created Earth's moon, ejected debris that coalesced into Charon. This collision displaced material into orbit, which gradually clumped under gravity. Charon's surface features icy plains, canyons, and cryovolcanoes, hinting at internal processes and geological activity. Its large size relative to Pluto suggests millions of years of sustained collisions and gravitational interactions shaped their joint evolution. The smaller moons, Styx, Nix, Kerberos, and Hydra, are much tinier, measuring roughly 10 to 50 kilometers across. Their origins are debated. They likely arose from several mechanisms, including remnants of impact events, capture processes, or a combination of both. Some scientists suggest these moons originated from debris left over after the initial collision that formed Charon, then reassembled into multiple small bodies through accretion within Pluto's gravitational influence. Others propose they are captured objects, ice-rich remnants from the Kuiper Belt, the icy region beyond Neptune, trapped by Pluto's gravity during early periods of instability. Their orbital histories are complex and suggest chaos. Styx and Nix have irregular, inclined, and eccentric orbits, indicating they were probably captured or formed from scattered debris. Their shapes, more potato-like than spherical, imply they are rubble piles, loosely bound collections of ice and rock. Despite a long history of impacts, these moons have persisted, which hints at a relatively stable gravitational environment around Pluto. Features like mutual influences and resonances help maintain a delicate orbital balance, preventing collisions or escape. The idea that they originated from collision debris that later settled into orbits emphasizes the complex, turbulent past of this system. Over time, gravitational interactions among these moons, especially with Charon, shaped their current paths. Understanding their formation offers insights into early solar system chaos, violent impacts, debris accumulation, and capture events. These moons are relics of primordial material, largely unchanged since their formation, frozen in a distant corner of the solar system. They are remnants of a time when planetary bodies assembled amid violent collisions and unstable gravitational influences. Their properties help piece together processes that shaped the Kuiper Belt, planet formation, and the broader architecture of our solar system. Pluto's smaller moons exemplify the outer solar system's tumultuous history, a cosmic dance driven by gravity and chaos. Each moon silently bears witness to a tumultuous past that shaped this distant region. Their existence highlights that, even in the Kuiper Belt's cold darkness, collisions, accretion, and gravitational capture have left enduring marks. These moons form a mini but complex system, revealing primordial processes and ongoing evolution. They remind us that the outskirts of our solar system still hold many secrets waiting to be uncovered. Absolutely, the moons around Pluto have played a fascinating role in shaping its geology and, to some extent, its orbit. Pluto isn't alone out there. It's part of a complex system that includes its largest moon, Charon, along with several smaller moons like Styx, Nix, Kerberos, and Hydra. These celestial companions aren't just passive spectators. They actively influence each other's worlds in ways that are both subtle and profound. Take Charon, for example. It's almost half the size of Pluto itself, so much so that some astronomers consider the two to be a double system rather than a primary and a satellite. The gravitational dance between Pluto and Charon is unique and has major implications. Because their centers of mass lie outside Pluto's surface, they orbit each other in a way that creates a sort of shared gravitational environment. This tidal interaction causes phenomena akin to what we see with other moons and their planets, such as tidal heating. The friction generated by this gravitational tug-of-war can generate internal heat within Pluto and Charon, fueling geological activity beneath their icy surfaces. This tidal heating is a game-changer when it comes to understanding Pluto's geological activity. It can warm the interior enough to keep subsurface oceans liquid or generate enough heat to drive cryovolcanism, the icy equivalent of volcanic eruptions. This process might be responsible for some of the complex surface features NASA's New Horizons mission uncovered. For example, Charon's vast, smooth polar region called the Mordor Macula might be influenced by material transferred from Pluto or by geological processes driven by tidal heating. Meanwhile, the fact that Pluto and Charon are tidally locked, always showing each other the same face, further complicates their interactions, altering the distribution of heat and geological activity across their surfaces. But it's not just Charon. Other smaller moons also have their part to play. These tiny satellites moving in their own orbits around the Pluto-Charon system can induce gravitational perturbations. While their influence on Pluto's orbit is relatively minor compared to Charon, these small moons contribute to a delicate gravitational ballet that can lead to subtle shifts in orbital parameters over long periods. Changes in orbital eccentricity and inclination, for example, could have shifts that affect the distribution of surface stresses, perhaps even triggering resurfacing events or tectonic activity. And let's not forget about the implications for Pluto's orbit itself. The gravitational pull of its moons, especially in such a tightly knit system, can cause slight variations in Pluto's orbit over millions or billions of years. These tiny nudges, cumulative gravitational influences, might seem insignificant on short timescales, but over geological ages, they can influence how Pluto wobbles through space, how its insides respond, and even how its surface evolves. This gravitational cooperation or tugging impacts surface stresses and potentially its atmosphere, which is in a delicate balance with its surface conditions. In essence, the moons around Pluto don't just orbit in their little spheres of icy wonder, they're active participants in shaping a world that continues to surprise us. Their gravitational influence fosters internal heating, drives geologic activity, and subtly affects their orbits and surface features. The interconnected dance of Pluto and its moons illustrates a complex dynamic system, where even the smallest companions can leave a big mark on a distant world, adding yet another layer to the astonishing complexity of Pluto's environment. When we look beyond Pluto itself, its moons reveal intriguing mysteries related to water and life ingredients. The two main moons, Charon and Styx, each tell unique stories about this distant system's composition. Recent data suggests these moons might contain clues about essential ingredients for life, challenging the idea that they are only frozen remnants. Starting with Charon, the largest of Pluto's moons, it's not just a static icy sphere. Although mainly composed of water ice, geological features indicate activity. Large chasms and smooth plains hint at internal processes. Spectroscopic observations detect water ice on its surface, along with mineral components like ammonium salts and other compounds, which could only have formed or been altered through interactions with water or water-rich substances. Even more captivating are cryovolcanoes on Charon, volcanoes ejecting icy material instead of molten rock. These eruptions might deliver subsurface material, including water or water-ammonia mixtures to the surface. Such activity suggests beneath its icy crust there could be pockets of liquid or slushy water, maintaining internal dynamism. If true, Charon might harbour environments where water exists in some form, an essential ingredient for life. Turning to Styx, the smallest moon of Pluto, the picture is less detailed due to limited data. Nonetheless, scientists indicate its composition is rich in water ice. Spectral signatures support this. Styx does not currently show signs of cryovolcanism, but it could still contain vital ingredients like simple organic compounds or other substances, possibly delivered during formation or via impacts. The presence of water or life-related ingredients on these moons opens exciting possibilities. In our solar system, moons like Europa and Enceladus host subsurface oceans beneath thick ice shells. Finding water and related compounds on Pluto's moons suggests they could be similar worlds. If internal heat sources, such as radioactive decay or gravitational interactions, provide enough warmth, some regions might sustain liquid water beneath the surface. Organic and chemically active materials, coupled with water, are key ingredients for prebiotic chemistry. For example, in Charon's interior, a mixture of water, ammonia, and organic molecules could enable complex chemical reactions. These processes may produce more complex molecules or primitive life forms hidden beneath the icy crust. In the cold darkness at the solar system's edge, Pluto's moons are more than just icy satellites. They could be dynamic worlds harbouring essential ingredients for life. They challenge prior ideas of where life might exist and expand our understanding of its resilience. As future missions and telescopic observations improve data about these moons, scientists remain hopeful of discovering proof that life, or its potential, may not be limited to Earth or familiar planets. Instead, it might be quietly developing in Charon's concealed interior or hidden in reservoirs of water beneath Pluto's frozen shell. While data remains limited, the possibility that these moons contain water, organic compounds, or other life ingredients makes them prime targets for exploration. The idea that subsurface lakes or slushy pockets of water could exist beneath their icy shells raises the prospect of habitable environments far from Earth, Such environments would be protected from space's harsh conditions, offering some of the best chances to find prebiotic chemistry or even microbial life in our solar system. The study of Pluto's moons continues to challenge our understanding of where and how life could survive or originate. Discoveries of water ice, mineral changes, cryovolcanism, and organic compounds suggest these worlds are more than inert icy bodies. They might be active, chemically dynamic environments with potential to host life-supporting conditions, even if we have not yet observed direct signs of life. This evolving view underscores the importance of ongoing and future missions exploring these distant worlds. By studying their surface compositions, internal structures, and heat sources, scientists hope to determine whether these moons could sustain environments suitable for life. The mysteries of Pluto's moons inspire broader thinking about habitats where life might exist within our solar system and beyond. They remind us that the universe often defies simple assumptions, hinting that the building blocks of life might be more widespread than previously thought, even in the most remote corners of our cosmic neighborhood. Among the many surprises brought to light by the New Horizons mission, the detection of complex organic molecules on Pluto stands out as particularly intriguing. These organic compounds, which are carbon-rich molecules that form the building blocks of life, hint at a far more dynamic and chemically diverse world than previously imagined. When New Horizons swept past Pluto in 2015, it revealed a surface dotted with nitrogen, methane, and carbon monoxide ices, compounds that, under the right conditions, can lead to the formation of more complex molecules. But it wasn't just simple ices that caught scientists' attention. It was the presence of organic molecules, some of which are considered fundamental precursors to life as we know it. The spacecraft's instruments detected signatures of tholins, complex organic molecules formed when simpler compounds like methane and nitrogen are exposed to ultraviolet radiation from the sun or charged particles from space. These tholins give Pluto its reddish hue, coating many of its surface features with a layer of the organic tar. The reddish coloration, particularly prominent on regions like the Tombaugh Regio's bright heart-shaped formation, was initially puzzling. Now it's understood to be the result of chemical reactions driven by sunlight and cosmic rays transforming simple molecules into these more complex carbon-rich compounds. But the story doesn't end with tholins. Spectroscopic data suggest the presence of other organic molecules, including simple hydrocarbons and complex organics that might be related to molecules found in comets and the outer solar system. These molecules could originate from Pluto's interior or be delivered via impacts from comets and other icy bodies drifting from the Kuiper Belt. The detection of such organics implies active chemical processes are ongoing or have occurred in Pluto's past, reshaping our understanding of this distant world as not just a frozen chunk of ice, but as a chemically rich environment. The implications of these findings stretch far beyond surface chemistry. Organic molecules, especially complex ones, are essential ingredients in the chemistry of life. Their presence on Pluto raises fascinating questions. Could similar processes have taken place elsewhere in the Kuiper Belt or beyond? Might these molecules be part of a broader chemical network capable of fostering prebiotic chemistry if conditions were just a bit different? Moreover, Pluto's varied surface regions seem to tell a story of chemical evolution. The older, darker areas are coated with a variety of complex organics, while younger, brighter regions, such as the nitrogen ice plains, show fewer of these molecules. This distribution suggests ongoing chemical processing driven by seasonal changes, radiation, and possibly internal geological activity, which continually exposes new fresh ices and facilitates the formation of complex organics. Scientists also speculate that beneath Pluto's icy crust, there could be subsurface layers where more intricate organic chemistry occurs. The presence of internal heat, possibly generated by radioactive decay or tidal interactions with Charon, might keep some internal waters in a liquid state. These subsurface oceans could serve as environments where organic molecules could further react and perhaps even support simple life forms, although that remains speculative at this point. In the grand scheme of the solar system, Pluto's organic chemistry adds a new dimension to our understanding of icy worlds. It suggests that even at the fringes of our sun's reach, chemistry akin to what might be necessary for life is taking place. This discovery pushes scientists to consider the potential habitability of other distant icy bodies and the broad distribution of life's fundamental ingredients across the cosmos. Instead of a static, frozen world, Pluto emerges as a chemically active, evolving cryo-world, teeming with complex organics and dynamic processes that continue to surprise us, reminding us that even the most remote corners of our solar system are full of secrets waiting to be uncovered. The idea that Pluto could support microbial life might seem far-fetched at first. Located at the edge of our solar system in cold, harsh conditions, it appears inhospitable to life as we know it. However, exploring beyond initial assumptions reveals a more intriguing picture. Scientists have discovered that Pluto's environment might hold the necessary ingredients, hidden beneath its icy surface, that could allow for microbial life in some form. One of the most exciting findings from the New Horizons mission was evidence suggesting Pluto is not just a frozen, dead world, but one with complex geology and internal activity. The detection of cryovolcanoes or ice volcanoes hints at active processes beneath the surface. These cryovolcanoes are believed to spew out substances like water, ammonia, and methane, liquid or mist-like materials that could create underground habitats. If these subsurface channels exist, they could serve as potential refuges for microbes, protected from the extreme cold and radiation that dominate Pluto's outer layers. Scientists have also found signs of a possible subsurface ocean beneath Pluto's icy crust. Though still under investigation, clues such as the distribution of surface features and geological activity suggest a layer of liquid water might lie below the surface ice. Water is a crucial ingredient for life as we understand it. Even in such a cold environment, a salty subsurface ocean could remain liquid, thanks to pressure from overlying ice and antifreeze compounds like ammonia, which lower the freezing point of water. This hidden ocean could act as a vast isolated habitat, offering the right conditions, liquid water, energy sources, and vital minerals for microbes to survive. Earth's microorganisms thrive in extreme environments, deep hydrothermal vents, underground caves, and polar ice, where sunlight doesn't reach, but life persists by harnessing geochemical energy. If similar chemical energy sources are present in Pluto's subsurface ocean, it opens the possibility of a hidden biosphere existing there. Pluto's surface conditions are undeniably extreme. Temperatures can drop below -200 Rodelstes, making surface life highly unlikely without protection underground. The surface is covered by nitrogen, methane, and carbon monoxide ice, with volatile ices continually sublimating and condensing. Yet many Earth microbes endure extreme cold and radiation by residing deep underground or beneath thick ice sheets, sheltered from the worst environmental conditions. These microbes only need a niche with the right chemistry and liquid water to survive, even in such extreme environments. The chemical complexity of Pluto's surface materials adds another aspect to consider. Organic molecules, including complex compounds called tholins, have been detected on Pluto. These molecules are the building blocks of life and form when solar and cosmic radiation interact with simple molecules. Their presence suggests a rich chemical environment that could facilitate prebiotic chemistry. Over time, such chemicals might lead to more complex organic molecules, potentially giving rise to primitive life, or at least the basic ingredients for it. While direct evidence of life remains elusive, the ingredients for life seem to be present beneath Pluto's icy crust in its interior. It's an environment where water, organic molecules, and energy sources coexist, key components for potential microbial ecosystems. If life exists, or ever existed, on Pluto, it would likely be microbial, microscopic, and residing in protected underground oceans, where it could survive the coldest reaches of our solar system. This possibility sparks the imagination and emphasizes how much more there is to learn about distant worlds. Despite its small size, Pluto's mysteries hint at a more dynamic, potentially habitable environment than previously thought. The idea of life in the outer solar system remains an inspiring frontier, encouraging scientists to explore further, search deeper, and remain open to the resilience of life in the universe. Pluto's surface and subsurface conditions reveal a fascinating mix of contrasts that challenge our understanding of promising environments for complex activity or habitability. Compared to other celestial bodies, Pluto is an icy world once thought inert and static, but now known to be more active with processes still not fully understood. Its surface features a patchwork of terrains, icy plains, jagged mountains, glaciers, and dark regions. A striking feature is nitrogen ice glaciers that slowly flow, carving valleys and reshaping the landscape over geological timescales. These glaciers, along with methane and carbon monoxide frost patches, suggest active redistribution of volatiles driven by seasonal or longer-term cycles. These volatiles can sublime and condense, causing atmospheric fluxes that modify surface features and possibly contribute to a dynamic environment. However, what lies beneath is even more intriguing. Radar data, gravitational measurements, and surface morphology hint at a subsurface that could host a liquid layer, a salty, possibly subterranean ocean. The presence of a hidden ocean transforms Pluto from a cold, inert ice ball into a potential realm of internal activity. Such an ocean could remain stable for billions of years, possibly maintained by radioactive decay within the rocky core, providing energy for chemical reactions, and perhaps even life. When comparing Pluto to more promising environments like Europa or Enceladus, moons of Jupiter and Saturn, both similarities and differences emerge. Europa's icy shell covers a vast salty ocean beneath, heated by tidal flexing caused by Jupiter's gravity. Enceladus exhibits active cryovolcanoes ejecting water, salts, and organic molecules into space, directly revealing a subsurface ocean. These moons show ongoing signs of oceanic activity and potential energy sources, making them prime targets in the search for habitability. Pluto lacks the strong tidal heating present on Europa or Enceladus. Its internal heat appears to be declining, and its overall surface temperature colder, potentially limiting the extent of subsurface liquid water. Still, its geologically young surface and features like cryovolcanoes such as Right Mons suggest some internal activity persists, possibly driven by radioactive decay or other mechanisms. The transport of subsurface volatiles to the surface indicates ongoing internal processes. The chemical composition of Pluto's surface adds another layer of complexity. It hosts complex organic molecules, tholin-like substances, giving it a reddish hue and hinting at rich chemical processes. These organics might originate in the subsurface ocean or be formed through surface chemistry, providing potential building blocks for life. Surface-atmosphere interactions create cycles of material exchange that could foster complex organic chemistry over time. In considering environments promising for life, Pluto is akin to a frozen laboratory, an icy world that, despite its coldness, hosts energetic processes. Its surface and subsurface conditions reveal a dynamic planet with potential pockets of liquid, chemical richness, and energy sources, though less obvious than on Titan, Europa, or Enceladus. Challenges remain. Extremely cold temperatures, limited heat sources, and the absence of tidal flexing could make Pluto less hospitable or less active. Yet, geological activity, evidence for an internal ocean, and complex organics suggest that even at the solar system's edge, Pluto may host environments more promising than previously thought. Pluto urges us to broaden our perspective, recognizing that environments suitable for life aren't limited to warm, tidally active worlds. Sometimes an icy, distant, seemingly frozen planet can be a hidden treasure, brimming with activity and mystery waiting to be uncovered. As we peel back the layers of Pluto's complex environment, one intriguing piece of the puzzle involves the role of comets and Kuiper Belt objects in delivering organic materials to this distant world. The Kuiper Belt, a vast, icy region extending beyond Neptune's orbit, is teeming with small, icy bodies, some of which are remnants from the formation of our solar system. These icy travellers, along with comets that occasionally journey inward, are like cosmic couriers, ferrying a rich cargo of organic compounds, water ice, and other complex molecules across the solar system. Every year, countless comets and Kuiper Belt objects make their journeys through the solar system, some passing close enough to Pluto to deposit their icy cargo on its surface. These objects are like sandblasters of the distant wilderness, colliding with Pluto at velocities that allow them to deliver their organic payloads without destroying them outright. When these icy bodies approach Pluto, they heat up just enough for sublimation to occur, turning some of the ices directly into gas, which then interacts with Pluto's surface and atmosphere. This process isn't just surface level, it's a way of sneaking precious organic molecules deep into the coating of the dwarf planet. Once these organics are deposited on Pluto's surface, they can undergo a variety of transformations driven by radiation from the Sun's distant rays, cosmic rays, and Pluto's own internal processes. Over time, these interactions can lead to the formation of more complex organic compounds, building blocks that are fundamental to the emergence of life as we know it. It's almost poetic to think that Pluto, in its cold, distant orbit, is quietly accumulating molecules that could someday be the foundation for prebiotic chemistry. Furthermore, the influence of these incoming bodies isn't limited to surface delivery. Many cometary and Kuiper Belt object impacts are energetic enough to crack open Pluto's icy crust, potentially creating pathways for subsurface liquids to emerge or facilitating the exchange of material between the interior and surface. This ongoing exchange is vital because it suggests that Pluto's interior may harbour liquid water or slushy layers beneath its icy veneer, regenerating its surface with fresh material and potentially harbouring the chemical reactions necessary for life. The material delivered by comets and Kuiper Belt objects isn't only rich in organics. It often includes water ice, ammonia, methane, and other volatiles, substances that play a critical role in shaping Pluto's atmospheric processes. As these materials sublimate from impacts and surface layering, they feed Pluto's tenuous but active atmosphere, which cycles these compounds through sublimation and condensation, creating a dynamic interface between the surface and space. This continuous exchange shapes Pluto's atmosphere, driving weather patterns and perhaps leading to seasonal shifts that influence surface features over time. Scientists believe that this continual infusion of organic material boosts the likelihood that Pluto's environment remains chemically active, rather than static. The added complexity of these organic molecules could influence the geochemistry of Pluto's surface and subsurface layers, hinting at the potential for chemical diversity that might, in some distant epoch, be conducive to prebiotic chemistry. The story of Pluto is intertwined with these small icy bodies drifting beyond Neptune. Each impact and each organic molecule delivered tells a story of cosmic recycling, an ongoing process where ancient icy remnants from the dawn of the solar system collide with the distant world, enriching it with organic and volatile compounds. This could explain why Pluto surprises us so much. It isn't just a cold, inert dwarf planet at the edge of our solar system, but a dynamic, chemically rich world, constantly being renewed and reshaped by the silent, persistent work of these small cosmic visitors. Future missions are crucial for understanding Pluto's habitability beyond data from New Horizons. To assess if this distant world could support life, missions must explore beneath its icy crust, analyze atmospheric chemistry, and examine possible subsurface liquid layers. These efforts will reveal more of Pluto's secrets and expand our understanding of habitability in the outer solar system. One strategy involves deploying landers or robotic drills to penetrate Pluto's ice, accessing subsurface layers where liquid water might exist as an ocean or brine. Understanding the composition, salinity, and temperature of these hidden waters could indicate their potential to support microbial life. Similar to icy moons like Europa and Enceladus, Pluto may harbour a subsurface ocean warmed by internal heat or gravitational interactions with Charon or other bodies. Confirming even tiny pockets of liquid water would significantly increase its habitability prospects. Future missions could also carry advanced spectrometers to analyse Pluto's atmosphere with greater precision. Detecting complex organic molecules, crucial ingredients for life, in its thin, hazy skies would provide clues about its chemical environment. Studying atmospheric chemistry and volatile cycles involving nitrogen, methane, and carbon monoxide would shed light on whether Pluto's environment has supported or could support biological processes. Understanding these cycles helps evaluate if Pluto possesses the necessary ingredients and energy sources for life. Enhanced imaging capabilities are equally vital. High-resolution cameras and stereoscopic mapping tools could identify regions of geologic or cryovolcanic activity, suggesting internal heat and ongoing processes related to habitability. Detecting areas where ice and organics are mixed, possibly in deposits, might reveal prebiotic environments. More detailed surface maps will guide landing site selection or sample collection, increasing chances of finding biosignatures or chemical signs of past life. Orbiters with ice-penetrating radar are essential for mapping Pluto's crust and searching for melt pockets or liquid reservoirs deep beneath the surface. These instruments can reveal layered structures or evidence of subsurface melting, indicating processes that might sustain liquid environments over geological timescales. Detecting such features raises questions about internal heat sources, radioactive decay, tidal stresses, or other mechanisms that might keep subsurface regions warm enough to support habitability. Hybrid missions combining orbital reconnaissance with landers or rovers offer a comprehensive approach. a lander could analyze surface samples directly, examining mineralogy, organics, and potential biosignatures, molecular indicators of life or prebiotic chemistry. Rovers or autonomous vehicles could explore diverse terrains, seeking environments most likely to harbour life. This integrated strategy would provide valuable context and in situ data, deepening our understanding of Pluto's habitability potential. International collaboration could accelerate exploration. Sharing data and resources would enable complex multi-objective missions probing Pluto's crust, atmosphere, and subsurface lakes within a single platform. Coordinated orbital and lander missions would maximize scientific return and reduce costs, tackling multiple goals simultaneously. Such efforts would enhance our capacity to detect environments capable of supporting life. Ultimately, understanding Pluto's habitability depends on deploying a range of instruments and mission concepts to reveal its hidden layers, chemical makeup, and internal heat sources. Each advancement increases our knowledge, bringing us closer to determining whether this distant world could harbour life. Once considered a cold, dead planet, Pluto's mysteries might soon challenge that notion, revealing potential habitats in its hidden depths. This prospect fuels curiosity about extraterrestrial life and broadens our understanding of planetary habitability in the outer solar system. In summary, future exploration should focus on probing beneath Pluto's crust for liquid water, analysing atmospheric chemistry for organic molecules and volatiles, imaging for geologic activity, mapping internal structures with radar, and conducting in situ surface analyses. Combining these methods within collaborative international missions promises to uncover whether Pluto has or ever had the capacity to support life. Each technological step enhances the likelihood of discovering habitable environments, even billions of miles away, transforming our perception of extraterrestrial life possibilities and advancing planetary science and astrobiology's future. Beyond the familiar planets and past Neptune's orbit lies the Kuiper Belt, a vast, icy region filled with leftover building blocks from the solar system's formation, comets, dwarf planets, and smaller bodies. It resembles a cosmic debris field and is a relic of over 4 billion years of solar history. Extending from about 30 to 50 astronomical units from the Sun, it lies beyond Neptune. Objects in the Kuiper Belt are mainly composed of frozen gases and rock similar to comets. These remnants either never formed into larger planets or were ejected during planetary formation. Scientists suspected its existence before observations confirmed it, revealing a distant, cold area filled with icy objects. The most famous Kuiper Belt object is Pluto, discovered in 1930. Initially classified as the 9th planet, it captured public and scientific attention. Its orbit is elongated and tilted, unlike the more circular paths of the main planets. This unusual orbit contributed to its reclassification as a dwarf planet in 2006. Despite this, Pluto remains crucial in understanding the Kuiper Belt's diversity and complexity. Pluto's orbit is eccentric and inclined, causing it to sometimes come closer to the Sun than Neptune, and other times drift farther away. Its path results from gravitational interactions with other Kuiper Belt objects and larger planets. Studying Pluto's orbit provides insights into the gravitational history and migration of objects in this remote region, making Pluto a representative of the icy worlds in the belt. Pluto's surface and interior are particularly intriguing. Its landscape features plains, towering ice mountains, and vast glaciers, indicating geological activity. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a surprisingly dynamic world, far more complex than expected. Instead of being a cold, inert body, Pluto shows signs of internal heat driving geological processes. Evidence suggests Pluto may host a subsurface ocean of liquid water, kept warm by residual heat and tidal forces. This hidden ocean raises the possibility of conditions suitable for microbial life, making Pluto of astrobiological interest. Its surface also contains complex organic molecules, hinting at chemical processes that could be precursors to life. Understanding Pluto's story offers insights into the primordial environment of the early solar system. The Kuiper Belt, with Pluto at its core, acts as a preserved record of planetary formation. Studying Pluto and similar objects helps scientists understand how the solar system originated, how organic molecules are distributed, and why icy worlds remain active billions of miles from the Sun. Pluto's significance extends beyond its location. it helps reveal broader narratives of planetary evolution. It exemplifies the resilience of icy bodies at our solar system's edges despite harsh conditions. Pluto illustrates the complexity and diversity of Kuiper Belt objects, serving as a key to understanding this distant region. In essence, Pluto acts as a prototype and window into the early solar system. Its characteristics reveal processes that shaped the outer solar system and still influence these icy worlds today. Studying Pluto enables scientists to reconstruct planetary migration and the persistence of organic molecules in cold environments. The Kuiper Belt, with Pluto as its flagship, offers vital insights into the solar system's past. It illuminates planetary origins, the presence of organic compounds, and the potential for life in extreme environments. By examining Pluto's surface, orbit, and interior, researchers deepen their understanding of how this frozen region remains active and evolving. Pluto's place in the Kuiper Belt emphasizes its importance not just as a distant body, but as part of a larger cosmic story. Its history and ongoing activity provide crucial clues about how the solar system formed, planetary migration, and the possibility of extraterrestrial life. The Kuiper Belt remains a frontier of discovery, with Pluto standing as a symbol of our quest to understand our place in the universe. Pluto's orbit is one of the most revealing clues about its mysterious origins and the story of our solar system's early days. Unlike the planets that follow more circular, predictable paths around the Sun, Pluto's orbit is highly eccentric and inclined, meaning it deviates significantly from the plane of the solar system and varies in distance from the Sun, sometimes closer, sometimes much farther out than Neptune. This irregular orbit isn't just a quirky feature, it's a hint that Pluto's history is unique. When astronomers first discovered Pluto in 1930-ish, they believed it might be a scaled-down version of the other planets, formed in the same orderly process. But as more was learned about its peculiar orbit, cutting across Neptune's path and with a tilt of about 17 degrees, scientists realized it didn't quite fit the story of a planet that formed in the same calm, gentle way as Earth or Jupiter. Instead, it suggested that Pluto's position and trajectory resulted from a turbulent childhood, involving gravitational tug-of-wars and cosmic dance moves with other icy bodies. Diving deeper into what that orbit says about its origins, it's believed that Pluto is a member of a vast swarm of objects called the Kuiper Belt, an icy realm beyond Neptune filled with remnants from the solar system's formation. These objects never cleared their orbits of debris like the gas giants did, so they're more like cosmic leftovers or building blocks that never quite made it into planets. The eccentric and inclined orbit of Pluto hints that it was likely pushed around by the gravitational influences of other Kuiper Belt objects, or perhaps even by Neptune itself early in its history. Over time, gravitational interactions could have nudged it into its current elongated path that swings over and under the average plane. Moreover, the orbit's shape and tilt suggest that Pluto's ancestors might have formed even farther out, in a more tumultuous part of the solar system, where interactions with countless other icy bodies were common. It's kind of like a cosmic game of bumper cars, with countless objects bumping into each other and exchanging energy. Whenever a small object like Pluto was jostled closer or pushed out, its orbit was altered, and over billions of years, this led to its distinctive, highly elliptical path. Another fascinating piece of the puzzle comes from the fact that Pluto's orbit sometimes crosses that of Neptune, which raises interesting questions about its stability and history. Despite the crossing, the orbits are configured in such a way that they avoid collisions because of a gravitational resonance. Pluto orbits twice for every 3 orbits that Neptune completes. This resonance acts like a cosmic safeguard, locking their paths into a stable dance that's been maintained for millions of years. Such a resonance indicates that Pluto's orbit was not just randomly set, but was shaped by precise gravitational interactions early in the solar system's history, hinting at a complex dynamic past. All of this tells us that Pluto wasn't born in the same calm, orderly neighbourhood as the main planets. Instead, it's a bit of an outsider, an icy relic, shaped and moved by gravitational forces and cosmic chaos, holding clues about a time when the solar system was a more crowded, tumultuous place. Its orbit is a record etched into the fabric of space, whispering stories of celestial encounters, migrations, and the chaotic dance of the early solar system. In a way, Pluto's strange path through the dark reaches of space gives us a glimpse into the turbulent past that shaped our cosmic neighbourhood. revealing that even the smallest, most distant objects can tell grand stories about the origins of our solar system. Pluto stands out remarkably among the countless objects drifting at the edge of our solar system in the Kuiper Belt. While this region is filled with icy bodies, many are small, dark, and simple in composition. Pluto, however, defies this typical description with its complexity and diversity, making it a true cosmic anomaly. First, size. Pluto is about 2,300 miles across, roughly two-thirds the size of the Moon, and nearly twice as large as many Kuiper Belt objects. Its substantial diameter means it has enough gravity to pull itself into a nearly round shape, initially leading to its classification as a planet before reclassification as a dwarf planet. Most other Kuiper Belt objects are much smaller, just a few miles across, and often irregularly shaped because their weaker gravity cannot mold them into spheres. However, size isn't the only factor that makes Pluto stand out. Its surface reveals an astonishing mosaic of terrains, thanks to active geology. It features vast plains of nitrogen ice, mountain ranges of water ice hundreds of feet high, and intricate surface patterns. These landscapes indicate geological and possibly atmospheric activity that is rare or absent in most objects in this region. Many Kuiper Belt objects are frozen remnants, coated in dark, dusty ice with little change. In contrast, Pluto is surprisingly dynamic. Its surface is reshaped by sublimation, ice flows, and likely cryovolcanoes that spew icy material instead of molten rock. Regarding atmospheric composition, Pluto again differs sharply. Most Kuiper Belt objects are frozen in a state of perpetual ice, with little to no atmosphere. Pluto sports a thin, layered atmosphere primarily of nitrogen, with traces of methane and carbon monoxide. During its closest approach to the Sun, the atmosphere expands and thins as gases escape into space. When it drifts away from the Sun, it cools and the atmosphere condenses back onto the surface. This cycle of atmospheric change, driven by solar heating, is unusual among icy objects. Most others have no detectable atmosphere, or maintain a tiny permanent layer. What makes Pluto even more extraordinary is what lies beneath its icy crust. Evidence suggests that beneath the surface might be a subsurface ocean, a hidden sea of liquid water kept warm by radioactive decay and possibly tidal heating. This underground ocean could harbour microbial life, a captivating possibility. Most other Kuiper Belt objects are too small or cold to support such internal liquids. Their interiors are likely just frozen ice or rock, inert and frozen in time. Add to this the organic molecules observed on Pluto's surface, complex compounds that are chemical precursors to life. Their presence hints at a rich chemistry capable of prebiotic processes. Although these organics are common in many Kuiper Belt objects, Pluto's size, active surface, and dynamic atmosphere make these molecules even more intriguing. Compared to its Kuiper Belt neighbours, Pluto is like a vibrant metropolis amid a quiet, icy wilderness. It's larger, more geologically active, and chemically richer. It teases us with the chance that more complex worlds exist out there. Objects blending icy, rocky, and possibly habitable qualities in ways that challenge previous understandings of the outer solar system. Pluto isn't just a distant dwarf planet, it's a shining example of the profound diversity and hidden depth of our cosmic neighbourhood. The origins of Pluto are shrouded in mystery and continue to spark debates among scientists. When astronomers first spotted this distant, icy world, many wondered how such a peculiar object came to inhabit the outskirts of our solar system. There are a few prevailing theories, each trying to piece together Pluto's unique story, whether it was born where it currently resides or caught in a cosmic game of gravitational tug-of-war. One widely accepted idea is that Pluto is a relic from the early days of the solar system. During that time, the region beyond Neptune was a chaotic playground filled with countless icy bodies, what some call the Kuiper Belt. This vast, donut-shaped zone is teeming with small icy objects, remnants of the primordial building blocks that didn't quite make it into the formation of larger planets. According to this theory, Pluto originated in this frigid zone and formed as a small icy planet, much like a miniature version of the gas giants, but without the gaseous envelope. Its composition and surface features, crystal-clear ice layers, organic molecules, and perhaps even internal heat, stand as clues that it has a long, storied history as a primordial object. However, things get a little more complex when considering how Pluto's current orbit and position came to be. It doesn't orbit the Sun in the same plane or the same kind of natural path that the planets follow, which hints at a more complicated past. Some scientists propose that gravitational interactions with other objects in the early solar system could have nudged Pluto into its current place. Over billions of years, interactions with Neptune and neighbouring Kuiper Belt objects might have slightly shifted Pluto's orbit. Some suggest that Pluto was once part of a larger planetary body that got broken apart in a collision. This colossal impact could have shattered a bigger object into smaller pieces, which later coalesced into Pluto and its moon, Charon. Another fascinating theory involves the idea that Pluto was originally a secondary body captured by the Sun's gravity rather than forming in place. In the chaotic environment of the young solar system, objects sometimes get caught in gravitational grips, much like a planet capturing a passing asteroid. For Pluto to be captured, it would have to have lost enough energy during close encounters with other bodies, or perhaps be slowed down by gas or dust present in the early solar system. Although capture mechanisms like this are complex and not as straightforward as natural gravitational accretion, there's evidence that such events might have occurred in other star systems, making it a plausible scenario here as well. Some scientists also explore the possibility that Pluto didn't form solely from the planetesimals in the Kuiper Belt, but rather it may have migrated inward or outward after initial formation. Its current orbit suggests a history of shifting, possibly due to interactions with Neptune's gravity. During such migrations, Pluto could have originated farther out, then been pulled into its present orbit through gravitational resonances with Neptune, locking it into a stable, though somewhat elongated, orbit. This dance with Neptune could have stabilized Pluto's position, preventing it from drifting away entirely while also shaping its eccentric orbit. All these theories highlight the complex and dynamic history of Pluto. Whether it's a primordial relic, a captured wanderer, or a fractured remnant of a larger body, what's clear is that Pluto's story is deeply intertwined with the tumultuous history of our solar system's formation. Its peculiar orbit, unique surface features, and the discoveries made by the New Horizons mission continue to challenge our understanding, reminding us just how much there is yet to learn about this enigmatic world at the edge of the solar system. Studying Pluto opens a window into the distant past of our solar system, offering clues about how planets and other celestial bodies formed and evolved billions of years ago. Because Pluto is so far from the Sun, frozen in a cold, distant frontier, its surface and internal composition have remained relatively unchanged for eons. This preservation provides scientists with a natural time capsule, revealing insights into the conditions that existed during the early days of the solar system. When we examine Pluto's surface, we find a surprisingly diverse landscape. Massive mountain ranges, icy plains, smooth nitrogen glaciers, and even regions with complex organic molecules. These features hint at a history of geological activity that persisted much longer than scientists initially expected for such a small, distant world. Unlike many other small celestial bodies, Pluto seems to have retained internal heat that fuels ongoing geological processes. This suggests that early on, when the solar system was still in its formative stage, Pluto had enough internal energy to sustain activity over billions of years, which might have been common among other icy bodies as well. One of the most striking discoveries from Pluto is the presence of a potential subsurface ocean. This hidden water layer, sandwiched beneath a shell of ice, could have formed early on due to radioactive decay and gravitational interactions. The existence of a persistent liquid beneath the surface indicates that Pluto's interior was capable of retaining heat and maintaining a state of partial liquefaction for extended periods. This is a vital piece of the puzzle because subsurface oceans are believed to be possible habitats for life, and their presence on Pluto raises questions about how common such environments might be on other dwarf planets and moons throughout the Kuiper Belt. Moreover, the organic molecules detected on Pluto, including complex hydrocarbons and tholins, are remnants of chemical processes that began in the early solar system. These molecules are the building blocks of life as we know it. By studying the distribution and composition of these organics, scientists can trace how basic chemical building blocks migrated or were synthesized during the solar system's infancy. This sheds light on how planetary bodies acquired their chemical riches and helps us understand the prebiotic chemistry that might have been widespread across the early solar system. The insight into Pluto's cryovolcanoes and surface renewal processes also offers parallels to other icy worlds in the outer solar system. These features serve as evidence that even small, cold worlds can sustain internal heat and activity long after their formation. That challenges previous assumptions that only larger planets and moons could have active geology. Recognizing this opens new avenues for understanding the dynamics of early planetary body formation, especially in the frigid outskirts of our solar system. Studying Pluto also informs models about how the solar system's initial disk of material was distributed and how its small bodies migrated and interacted. Its unique composition and geology provide data points for simulations that aim to recreate the conditions of the early Kuiper Belt. These models can, in turn, tell us about the processes that led to the formation of planets, dwarf planets, and icy bodies. In essence, Pluto acts as a distant, ancient record of the early solar system, a place where we can observe the lingering traces of the processes that shaped our planetary neighbourhood. Every discovery about this icy world not only reveals its own story, but also helps us piece together the broader narrative of how our solar system came into being, an entire story written in the frozen landscapes at the edge of our sun's domain. The discoveries made by the New Horizons mission have profound implications for our understanding of the solar system and the processes that shape celestial bodies. One of the most striking revelations is that Pluto is far more dynamic and complex than previously thought. Its diverse terrain, from vast ice plains to towering mountains, suggests an active geological history that challenges the idea of dwarf planets as static remnants of planetary formation. This redefines our understanding of what small, distant worlds can do, indicating that even bodies considered minor can host ongoing geological activity. The potential existence of a subsurface ocean beneath Pluto's icy crust opens exciting possibilities for habitability. This hidden reservoir could provide a stable environment where water, nutrients, and energy sources necessary for life might exist. If Pluto maintains a subsurface liquid water layer, it implies that many other icy bodies in the solar system, such as moons of Jupiter and Saturn, may also harbour such oceans. This broadens the scope of astrobiological exploration, suggesting that life could exist in places previously considered unlikely, expanding the potential habitats beyond Earth-like planets. Detecting organic compounds on Pluto has significant implications for understanding the building blocks of life. Organic molecules are essential for developing life as we know it, and their presence on Pluto indicates that complex organic chemistry is not limited to Earth or inner solar system bodies. These molecules might be widespread across the cosmos, delivered by comets and asteroids, making the raw ingredients for life abundant even in the most remote parts of our solar system. This supports the idea that the conditions for life are common, and that the solar system's early environment may have been conducive to habitability. The active surface processes and dynamic atmosphere observed on Pluto challenge previous assumptions that small, distant worlds would become inert over time. Instead, it appears that internal heat, possibly from residual formation heat, radioactive decay, or tidal heating, sufficiently powers geological activity. This ongoing activity necessitates revisions to models of planetary evolution, showing that smaller planets and icy worlds can remain geologically active far longer than once thought. It highlights that planetary activity isn't exclusive to large planets, but can occur in smaller, colder worlds, reshaping our expectations for planetary dynamics in the outer solar system. The diverse terrain of Pluto, including cryovolcanoes and nitrogen ice flows, suggests that volatile compounds are still moving and actively reshaping the surface. This insight into how ices behave under extreme cold conditions informs our understanding of surface renewal processes. It also provides comparative insights for other icy bodies, helping scientists understand how surface features can persist and evolve in such environments. Beyond scientific insights, these findings prompt a reassessment of where to search for life beyond Earth. Moons like Europa and Enceladus are known candidates, but Pluto and similar trans-Neptunian objects now join the roster as compelling exploration targets. This new knowledge encourages further missions to these distant worlds, aiming to uncover their potential for hosting life. Overall, Pluto is no longer seen as a static, frozen remnant, but as a lively, complex world. Its geologic activity, chemical diversity, and possible subsurface ocean serve as a window into planetary evolution and habitability in the outer solar system. These revelations remind us that even remote, icy worlds can hold surprises, challenging our view of the universe and expanding the horizons of astrobiology. They suggest that habitable environments may be more common and widespread than previously thought, reshaping humanity's understanding of place and potential for life in the cosmos. Pluto's discovery and reclassification challenged our fundamental understanding of what defines a planet. When Clyde Tombaugh first spotted this icy world in 1930, it was celebrated as the 9th planet, fitting neatly into the recognised planetary family. However, as technological capabilities advanced and our knowledge of the cosmos deepened, Pluto's unique features became more apparent, prompting scientists to reconsider the criteria for classifying planets. One major challenge Pluto presents is its size. With a diameter of roughly 2,300 miles, it is tiny compared to Mercury or Venus. Its mass is a small fraction of Earth's, and it resides amid countless other icy bodies in the Kuiper Belt. This raises questions. Should celestial bodies be classified mainly by size, or should other qualities such as orbit or composition take precedence? The old definition emphasized a planet's ability to clear its orbit, but Pluto is too small and gravitationally insignificant to meet that standard. Pluto's orbit also complicates its classification. Unlike the more circular, relatively aligned orbits of classical planets, Pluto's path is eccentric and inclined. It sometimes comes closer to the Sun than Neptune, then strays farther out. This orbital behaviour resembles many Kuiper Belt objects, suggesting Pluto might belong to a population of small icy bodies rather than being a lone dominant planet. Beyond size and orbit, Pluto's composition adds complexity. Its surface features a mix of ice and rock, with diverse terrains, some smooth, others cratered, and some showing signs of cryovolcanism and active geology. These features imply a dynamic world with internal processes that continue to shape its surface. This activity contradicts the traditional image of planets as inert, cooled spheres, raising questions about what geological activity signifies in classifying celestial bodies. Additionally, Pluto has 5 known moons, notably Charon, which is nearly half of Pluto's size. Charon and Pluto are locked in a mutual tidal orbit, creating a double system more akin to a binary pair than a standard planet-moon relationship. This relationship challenges the notion that a celestial body with a large moon orbiting the Sun is necessarily a planet. It raises the question, does this make Pluto part of a binary system rather than a planet? These factors, small size, unusual orbit, active geology, and satellite structure, blur the traditional categories. The International Astronomical Union, IAU, defines a planet as an object that orbits the Sun, is spherical under its own gravity, and has cleared the neighbourhood around its orbit. Pluto meets the first 2 criteria but not the third, leading to its reclassification as a dwarf planet. As astronomers discover more objects like Pluto, such as icy bodies, rogue planets, and eccentric orbit objects, our definitions may need to evolve further. Pluto challenges us to rethink the criteria for planetary status, and to embrace a more nuanced understanding of these distant worlds. It underscores the diversity and complexity of our solar system beyond the neat categories once envisioned. In response, scientists continue to refine classifications, seeking to better understand the rich variety of objects in our cosmic neighbourhood. Word count, 533. Despite everything we've uncovered about Pluto, many mysteries still linger in the shadows of this distant world. Its complex surface, vibrant atmosphere, and intriguing interior raise just as many questions as they answer. For example, scientists are eager to understand the true extent and nature of Pluto's subsurface ocean. Is there a vast liquid sea hidden beneath its icy crust, lingering in a warm, pressurized pocket? Or is the ocean more localized, perhaps confined beneath certain regions? And if it does exist, could it harbor the ingredients necessary for life? That question continues to inspire curiosity because, on Earth, where liquid water exists, life thrives. Could the same be true for Pluto's icy depths? Another lingering mystery revolves around the organic compounds found on its surface. These complex molecules, known as tholins, give Pluto its reddish hue and hint at rich chemical processes. But where exactly do these organics originate? Are they delivered by comets and space dust? Or are they produced in situ through chemical reactions driven by solar radiation or internal heat? Understanding the origin and distribution of these organics could shed light on the chemical evolution of not only Pluto but of other icy bodies in the solar system as well. The atmosphere of Pluto also raises more questions than it answers. For a body so far from the Sun, its thin, nitrogen-rich atmosphere is surprisingly dynamic. What processes sustain this tenuous envelope over geologic timescales? How does it interact with the surface, migrating across the landscape, creating temporary weather patterns, or forming frost deposits? And what happens during seasonal changes as Pluto moves along its highly elliptical orbit? Does its atmosphere grow denser at certain times, or does it freeze out entirely at its farthest points from the Sun? Understanding these atmospheric dynamics could offer valuable insights into how climates evolve on other small icy worlds. The origins and evolution of Pluto's moons also pose tantalizing questions. Charon, its largest moon, shares a textured history with the dwarf planet, but many details remain elusive. How did these moons form? Are they the remnants of a colossal impact, or did they coalesce from the same debris that formed Pluto? What is their internal composition? And do they have their own subsurface oceans or geological activity? Exploring these questions could help us understand how multiple bodies interact and evolve in the distant reaches of the solar system. Furthermore, scientists are curious about the full extent of Pluto's geological diversity. The New Horizons mission revealed towering ice mountains, vast plains, and possibly cryovolcanoes, but many regions remain unexplored or poorly understood. How active is this geological landscape? Does Pluto still harbour internal heat that fuels ongoing surface reshaping? Are there hidden layers below the crust that could reveal clues about its past? Unlocking these secrets could help us picture how small planets and dwarf planets develop over billions of years. Perhaps most compellingly, researchers wonder what other surprises Pluto might reveal as technology advances. Could future missions uncover novel phenomena, perhaps even signs of past habitability or biology? As we continue to refine our instruments and understanding, the enigmatic charm of Pluto keeps beckoning us, urging us to look deeper and ask more questions. Every answer seems to lead to new mysteries, making Pluto one of the most fascinating worlds in our solar system's distant frontier. As the thrill of discovery ripples through the scientific community, new missions and technological advancements promise to unlock more secrets of Pluto. While New Horizons provided an unprecedented view of its surface and environment, the journey isn't over. Future explorations aim to deepen our understanding, showcase cutting-edge technology, and perhaps pave the way for missions to other icy bodies in the Kuiper Belt. One promising prospect is the proposed Arakoth reconnaissance mission, planned to revisit the Kuiper Belt in the coming decades. Although focused on a different target, similar technology could be adapted for future Pluto explorations. This mission would utilize advanced orbital and landing technologies, offering high-resolution imaging and in-situ analysis. Using sophisticated spectroscopy instruments capable of analyzing surface composition at a molecular level could help decode Pluto's organic materials with greater precision. Looking farther ahead, NASA's Pandora project is an innovative concept for a dedicated Pluto orbiter. It would feature a spacecraft equipped with high-definition cameras, spectrometers, and radar systems capable of penetrating Pluto's icy crust. The goal is to map its geology in detail, search for glaciers, and investigate a possible subsurface ocean with radar imaging. Technologies like ice-penetrating radar could reveal hidden oceans beneath Pluto's crust, confirming liquid water and assessing habitability. Advanced mass spectrometers could analyze Pluto's atmosphere and surface materials with unprecedented sensitivity, identifying complex organic molecules, assessing atmospheric chemistry, and searching for signs of biological activity. Laser altimeters could generate detailed topographic maps, revealing subtle landscape features and helping scientists understand ongoing geological activity. What role will upcoming telescopes play? The recently launched James Webb Space Telescope, JWST, can observe Pluto from afar with remarkable sensitivity. Although it cannot land or orbit, JWST can monitor seasonal changes, study atmospheric chemistry, and provide clues about surface processes. Its data complements in situ missions by identifying areas of interest for closer examination, guiding future spacecraft. Advances in propulsion technology could also drive exploration forward. Concepts like solar sails or ion propulsion systems might enable spacecraft to reach Pluto faster, allowing more extended and detailed missions. The development of miniaturized instruments and CubeSats offers another promising trend. Tiny stations with cameras, spectrometers, and radar could be deployed around Pluto or land on its surface. conducting localized studies and transmitting data back to Earth. International collaboration could amplify these efforts. European, Japanese, or Chinese space agencies might contribute instruments or mission components, expanding our understanding of Pluto and its place in the outer solar system. Sharing expertise and technology can lead to more comprehensive studies, broadening our knowledge of the Kuiper Belt. Finally, artificial intelligence, AI, and machine learning are set to revolutionize exploration. These tools can assist in mission planning, data analysis, and autonomous decision-making during voyages. They could help identify the most promising sites on Pluto before the spacecraft even arrives, ensuring every moment is maximized for discovery. These advancements point toward an exciting future, where Pluto transforms from a distant, mysterious world into a well-studied and fascinating part of our solar neighborhood. The quest to understand its mysteries is far from over. Each new mission and technological innovation brings us closer to unraveling the profound story of this icy world. Pluto's discovery and the incredible insights gained from its study have fundamentally reshaped our perspective on the Kuiper Belt and other small icy worlds at the outer edges of our solar system. When Pluto was first discovered in 1920, it was hailed as the 9th planet, a new distant world orbiting beyond Neptune. Its existence challenged astronomers to broaden their understanding of what constitutes a planet, leading to decades of debates, discoveries, and eventually the